Okay, welcome to the second week. And then this morning we started Kostas, and he'll tell us about complex Langevin, the emergent spacetime and the Lorentzian IKKT matrix wall, and so on and so on.
Okay,
Go ahead.
so I thank the organizers and particularly Dinjo for organizing this wonderful.
Jens.
Yes, okay.
That's appropriate.
Okay, so this is work that I'm doing with those fellows here, and here we are working over different continents together. And today I'm going to be discussing numerical simulations of the type 2B matrix models. I don't have to introduce it when speakers have already introduced it in previous talks. So let me just remind you that the model has been proposed as a non-perturbative definition in superstring theory. It is a model of matrices here, and then there are n by n matrices that are Hermitian, that transform like vectors, and the other ones that transform like Majorana-Weyl spinors. That's the bosonic part, the fermionic part. I'm just introducing terminology that I will be using later. And the feature of the model that I'm particularly interested in is that space-time emerges from the bosonic matrix degrees of freedom. The eigenvalues of A nu can be thought of as space-time coordinates. Therefore, this identification will allow us to study questions like the dynamical emergence of time, the dynamical emergence of space, the dynamical compactifications of extra dimensions of string theory, and the time evolution of the last dimensions of the universe. Keep pressing the button. So the emergence of space-time is a non-trivial dynamical issue that the model must satisfy. Time must be homogeneous and infinite extent in the Lorentzian limit. The number of large dimensions of space must be 3. Remember that we start from 10 dimensions and expand in a way consistent with cosmological models, at least at late times. Time and space must be real. It's not a priori set, so that must be a property of the emergent observables in the model. And the signature of the space-time geometry must be Lorentzian, at least at late times. So,
Sorry, stupid question. What does this time map is homogeneous mean? I mean,
we have eigenvalues that will be representing time, and this must be distributed homogeneously, not to be clustered, for example, or form disconnected parts. So you need in the Lorentzian limit that this distribution is given by density that is almost constant and extends in both directions.
Thank you.
Infinity. So
when you say number of large dimensions of space must be 3, if I look at the model, that's not obvious.
That is?
If I look at the model, it's not obvious, right?
It is not, yes, because we start from 10 dimensions. We have 9 spatial dimensions, and we want 3 of them to emerge large and the rest to stay small.
So that's a non-trivial conjecture.
It is highly non-trivial. No, it's not conjecture. It's something that we want to study if it actually occurs. Okay, so that is the scenario that we will be studying in this talk. So these are the questions that we will try to address in this talk, and these are effects that are non-perturbative, and we will resort to numerical simulations. So let me just remind you a little bit of this history of quote lattice string theory. There is a history where Monte Carlo simulations have been used to study singular models since 1998, 1999. And here are some people that have pioneered this: Konstantinos Anagnostopoulos, and some other people at the MPI. And mostly these were numerical studies of the Euclidean versions of models in 4, 6, and 10 dimensions, using simplified models so that they can be studied with the computer resources of those times. And the attempt was to understand the mechanism of the dynamical compactification of extra dimensions. And the scenario that one entertains and wants to find out whether it occurs is that these extra dimensions are compactified by a mechanism of spontaneous symmetry breaking of the original SOD rotational invariance of the model. Okay, remember we're talking now about Euclidean. And what has been found is that the fermion dynamics play a crucial role in the realization of such a scenario, and that the numerical simulations of the real model in more than 4 dimensions are pretty hard, because there is a strong complex action problem. In 2011, Nishimura, and Tsukino used the Gaussian expansion method, and there they found that indeed the SO10 invariance breaks down to SO3, and the 3-dimensional configurations must be dominating the path integrally. And in 2020, using brute force Monte Carlo simulations using the complex Langevin method to address the complex action problem, we produced results that were consistent with the Gaussian expansion method. So let me remind you a little bit how we want to address this question. As I said, the eigenvalues of A mu will be representing the time. Of course, this is this cartoon here assumes that the matrices are mutually commuting, and you see model 3 dimensions with a 6x6 matrix. And if you organize the eigenvalues in this way, you can get n points. Here we have 6 points in space-time, which as you increase n, they become more and more. And in the larger limit, you expect to have a distribution of them that will be a good approximation to time.
Sorry, what are you showing us? If D equals 3 means it's the supersymmetric 3-dimensional?
No, nothing. It's just kinematic.
Okay.
That's so that I can draw the cartoon. I have to use 3 dimensions. Okay, and to put a few points, I put n equals 6 to show 6 points. Yes.
So what's the probability distribution that you use for Monte Carlo?
Well, we'll go there. So, of course, this is a fuzzy space-time because the dominant configurations are not mutually commuting, so we cannot diagonalize them simultaneously. And this fuzziness is an important thing that one can measure in those simulations. So, in order to have an order parameter of whether this distribution is SOD symmetric or breaks that symmetry, we use this quantity here, this trace of product of those 2 matrices. And we call this the moment of inertia tensor for obvious reasons, because it reminds us of the distribution of the points in solids. And if you compute the eigenvalues, this will give you the size of the principal directions of this distribution and gives us scales of how fat the distribution is in those principal directions. So the scenario that we are, the simplest possible scenario that can occur to have this SOD realizing is that you take the larger limit and you find that D of those eigenvalues have expectation values that are large, and the rest of them remain small. So in that case, you can say that you have D large dimensions, D small large dimensions, and the rest are small. So, as I already mentioned, the fermion dynamics are the ones that induce the spontaneous symmetry breaking, and the fact that the effective partition function of the fermions is complex plays also a central role in the model. So first, we integrate the fermions. They're quadratic in the action, so that will give us in 10 dimensions a Pfaffian of this operator M, and this operator is complex. So this phase here fluctuates widely, and we have a complex action problem, but it's exactly those fluctuations that are expected to favor configurations of lower dimension. And Nishimura and Lorentzian pointed out that back in 2000, where they showed that the fluctuations of this Pfaffian reduce with the dimensionality of the configuration, and the fact that 2-dimensional configurations have 0 Pfaffian means that there is a lower limit to how small the dimensions can become. So two dimensions are completely excluded in this pattern.
But because
I don't understand that because probably I'm thinking in the wrong direction. But I mean, there are antisymmetric 2x2 matrices, which have non-zero Pfaffian. So why does Pfaffian be a zero for two-dimensional configuration?
Well, that is very old work. Let me not discuss it now. But it's a working term. I mean,
It's not 2x2 matrix. This script.
this is n squared by n squared.
Huge matrix.
It's a huge matrix. Yes.
but does this at any finite n, the SOD symmetry is preserved? So
Not necessarily.
why not? Because it's just a finite number of degrees of freedom,
Yes.
and the symmetry should be there if you sample the distribution according to.
No, but at each time we choose the principal directions. So it's like in the Ising model where if you want to compute the magnetization, you take the absolute value.
So you
So
are
that-
taking an absolute value.
Exactly.
Okay.
So that is every time we turn the axis so that they point in the principal directions, and that is when we measure the eigenvalues.
Okay, that's just my question. Just the same issue arises in the device.
So now the fact that this complex phase plays an important role as an idea, was enhanced by first of all studying models that have fermions completely quenched, like back in 1998. We called these the bosonic models, and there it was calculated that the SSP does not occur. Then later we put in dynamical fermions at dipole 4, but in that case the Pfaffian is strictly positive, and again we see no SSP occurring. And then later in 2015 we started the full 10-dimensional model, but with only the phase quenched.
So just to go back, when you're saying these lower dimensional models, are you taking the lower dimensional supersymmetric version with,
Yes.
with the fermions of that?
In this one, yes. Yeah, that's a supersymmetric model. That is not a supersymmetric model. This is without fermions. So here it's the 4-dimensional supersymmetric model, and that is the 10-dimensional supersymmetric model, but we quench the phase. So if you quench the phase, then there is no SSP. And of course, as I already mentioned, the Gaussian expansion method was already hinting that this scenario occurs. And here you see that when one takes a full dynamical fermion simulation, including the complex phase, and for that we use the complex Langevin method, then we are able to see that 3-dimensional configurations are favored. And this was a quite complicated work. These rows here are nothing but those eigenvalues normalized so that we minimize some systematic errors. But in order to define the model, as we will see, as I will be progressing in the following slides, we have to define several deformations to be able to do the numerical studies. And one has to make many extrapolations, and this is what you see in those plots. We have one extrapolation with those masses here, and one extrapolation here with this term here that I will explain later. So let me now go to the Lorentzian model. So in the Lorentzian model, we have this metric here, and in the path integral, we have the action here with an I. And again, we integrate the fermions, and we obtain the Pfaffian here. Now, the Pfaffian is a real polynomial, not strictly positive, but real. And the main source of a serious complex action problem comes from the I here in the bosonic action. So in order to define the model, we have to do some kind of analytic continuation. So first, we just make a redefinition. That's just a definition, so that the path integral looks more like Euclidean simulations, but it's not here. This is tilde here. And Asano, Nishimura, and Tsuchiya proposed to do this type of weak rotation to define the model. It is characterized by two parameters, S and K, representing a weak rotation that is independent of the embedding space and on the world sheet from the string theory. And particular values are when S and K are both 0, we have the model that we want to study, the Lorentzian model. And if you take both S and K equal to 1, then you go back to the Euclidean model. So you can make these paths in this two-dimensional parameter space and connect those two models where you like. So if we express the action now in terms of the created fields, we obtain this action here, S tilde, that has those spaces from the parameters S and K. And we also have to take care of the fermion operator M here, which in the end will only take the rotation of the time matrix, because as you can see here, the rotation of the space matrix and the time matrix put an overall phase here, which is irrelevant. So in this talk, I will be considering only the case where S and K are equal, and I'm going to be calling this parameter to be U. So we have a deformation that with this parameter, where U equal to 0 gives us the model that we want, that's the target model, and U equal 1 is the Euclidean model. So we can connect them via a line. And if you take observables that are analytic, then by using just the rotation on the complex plane in Cauchy's theorem, you can show easily that you expect that those expectation values, where you replace the fields by the rotated fields here, become U independent. And in fact, this is something that we also studied numerically, the case where we ignored the values in the boson model, and we calculated the expectation values of trace A0 square, that is the scale of the extent of time, and trace AI square, that's the scale of the extent of space. And we find that they are related in those two models exactly as they are expected from this simple argument. So what we conclude from this is that the IKKT model as it is will give us, since in the Euclidean model those expectation values are real, it turns out that space and time in the Lorentzian model are complex. And because we already know that this is, we have three-dimensional space-time in the Euclidean model, this is also what happens in the Lorentzian. And also the metric is not Lorentzian. So in order to obtain a real space and time, we consider adding these Lorentz invariant quadratic terms in the bosonic fields. And this was also studied before by those gentlemen here. Now we have a metric, so this is plus and minus sign here. And the model that we want to study is the one that we obtain after taking the Larsen limit, and then one can try to take this parameter gamma to go to 0. And the reason why we obtain something non-trivial is that you notice that when gamma is positive, then this action here is negative, so it is not well defined, and those two models cannot be connected anymore if one adds this term to the action. However, if you take gamma negative, or of course 0, then this equivalence still holds. Now, these models, classical solutions, were studied in 2000 by all those people, 2020, sorry, by all those people, and what they found, and the study, sorry, was numerical, what they found that was for gamma positive, one obtains real expanding classical solutions, whereas for gamma negative, the solutions do not apply. And the dimensionality on the classical level cannot be determined. One has to do, which is the quantum model to see what the dimensionality is, which ones are most in favor. And also as Stein-Eicher noticed in 2017, for gamma equals 0, that means when this term is absent, then the model has only commuting classical solution. So that's kind of tricky. But you will hear more by Jun in the next talk about that. So let me now set up the point of view that we use in Bose simulation. So in this talk, I will be considering only U equal to 0, that means the Lorentzian model, and the case where gamma is positive. In order to interpret the matrix configurations of space and time, the first step is to diagonalize A0 and consider its real eigenvalues to be ordered in ascending order here. So that these ones will represent time in a way that I will explain in a little bit. And when one does that, one finds that the non-trivial dynamical property of the system is that the space matrices in this particular case have a band diagonal structure. That means that the elements with big modulus are concentrated near the diagonal and they follow fast as we move away from the diagonal. So there is a little n here. It's not defined precisely, but except of course the results are a function of n later, where those blocks here capture the main matrix elements here, and you can do that for all 9 matrices. And if you consider the respective blocks at the same position in the diagonal, this is what we will be calling as space. And this will be related to a time by considering the similar block in A0, and this will be the time where this space occurs.
How fast do they fall off? Do the limits fall off?
I will show you some picture later, but well, it's not Gaussian, but it's something that you find the peak near the center, and then it falls off.
Is it roughly exponential?
Yeah, I'm not sure. Actually, we don't have such good data for flowers and fishes. This was studied before in a completely different model by Jun. I think it was exponential forward, or was it Gaussian?
We didn't try to fit it.
Oh, you didn't try to fit it, okay.
Well,
Yes.
Sorry, how big is little n compared to big N?
I mean, the scaling of, what is important is how little n scales with large n.
Sure.
And that is something to be studied. We don't know. So here's the precise definition of time that we will be using. Of course, it's not unique. Microscopically, you can find it in many ways. So what we first do is we average those, let's call them time coordinates over the block. And that will give us this a bar here. And because this will turn out to be complex when we complexify them in complex around, we take the modulus of 2 consecutive ones to give us the delta t. So we sum all those delta t's, and that will give us the time that this block is here.
This is a Lorentzian time.
This is something to be determined dynamically, but yes, for the phase space of the parameters that we will be studying, it will turn out to be real, therefore Lorentz. So, as I already mentioned, those alphas will become complex. So, if you take consecutive values of those matrix elements, this will have a phase. And if you take the expectation value of that phase, if time is real, this phase should be 0. So you want consecutive ones to be following the real axis. And with the weak rotation that I showed you before, if this angle turns out to be at this particular value here, then you will have obtained the Euclidean model. So this is what will be a signature of what type, what signature of metric we obtain here. Now, for a technical reason, it's good to have variables that respect the ordering of time independent of the values that they take. That is because we will use complex Lagrange. So Nishimura and Tsuchiya here made the change of variables going from alpha to those variables here I call tau. And the taus here can take any real value from minus infinity to plus infinity. And with this definition, we will keep the ordering here of the time variables from the smallest to the biggest one. So this will be the degrees of freedom that we will be using in the simulations. And of course, with all those change of variables, diagonalizing A0 will give us here a van der Monde determinant, and changing to those variables will give us a gauge fixing action that we have to add in the end. Now, another problem that we have to address is the so-called singular drift problem. And what happens is that if you consider the fermion operator, then many of its eigenvalues tend to near the origin. And since the drift has something to do with the inverse of that operator, that will give you a singular drift. So what we want to do in the simulation to avoid this problem is we will add a term that is quadratic in the fermions, and the deformation here will be governed by this parameter here, which we call MF. And the effect of this term, when MF is real, is to shift all the eigenvalues of the fermion operator to the right. Thus, all this accumulation here, instead of being in the origin, it shifts a little bit to the right. So from now on, whenever I refer to the fermion operator, it will include also this deformation here.
So it's not actually a mass term. It's a complex mass term.
Yes, it's quadratic in the fermions. I will try to motivate it in a few transparencies, but yeah.
What happens if you don't do that? You mentioned the name.
Yeah.
What's the problem?
Problems, I will say more about it later, but let me say it now. You see all those eigenvalues that accumulate here, they would accumulate here near the origin. So you will get many values that are not exactly zero, but they are very close to zero. And then you try to invert this operator. So you will get very many numerical errors from all these eigenvalues that are very close to zero, because you get the inverse.
You could have chosen an imaginary, or you could have chosen a complex area, which would have moved the.
So
would have moved any
this choice was
axis.
at least originally made only because it was more the simulations were it was better for the simulations. So that is the choice of here. But in principle, we have made many studies also putting an arbitrary face. So, but let me not go.
So in this choice of mass term, you're sort of breaking the symmetry
Yes.
by 7, 8, 9.
Yes. So unfortunately, this term breaks both supersymmetry and also breaks the rotational SO9 invariance down to SO6. Okay, so we have to live with that. And of course, in the end, after we take the larger limit, we have to take the gamma to zero limit, but we also now have to take the MF to zero limit. But remember that we did that successfully for the Euclidean model. So the principle is something that can be doable. Another remark is that if you take this parameter here to go to infinity, that freezes the fermions, which completely decouple, and you get the bosonic model. So this is a nice way to interpolate between the IKKT model and the bosonic model. So it is challenging to make this parameter small, because as we make it smaller and smaller, the eigenvalues approach the origin, and the conjugate gradient method that is used to compute the inverse of the operator takes much longer to converge. The singular drift problem of the complex Langevin is enhanced, and the CLM becomes unreliable. Therefore, that makes the need to go to larger n, which is an additional computation cost. And the reason why we need to take MF smaller than it was possible to do it in a straightforward way is that if MF takes the values that we are able to simulate, then we are still in the bosonic phase. We have similar results like in bosonic form.
Can you say what you mean exactly by the singular drift problem?
Later. So, in order to do that, we do a trick. So, the idea is that since the three-dimensional universe is expected to come out because of fermions, we want to enhance the fermions, and one way to do it is by suppressing the bosonic fluctuations. So what we do is we introduce one more deformation, and that deformation is within the quadratic bosonic term here, and we introduce here the parameter t, and as c becomes larger, it suppresses those dimensions, so some of the fluctuations of the bosonic matrices are suppressed, and we hope that as C becomes larger, then we will be able to enhance the fermionic effects more and more and be able to see their effect. So the motivation for doing this is described here. The bosonic phase is characterized by the strong attraction of values. Okay, and we have the value of the determinant here. Whereas the Pfaffian has the effect of making this attraction weaker. And if the number of bosonic matrices is increased, the attractive forces between the eigenvalues is also increased. And the other way, if it is decreased, we make this attractive force decrease. Yes.
I have a question about the C.
Yes.
I mean, this is the phenomena that's the most important qualitative phenomena that you want to see. That the eigenvalues of
yes.
many of the dimensions don't spread. But
so,
is it not dangerous to put it in?
Yes, it is dangerous, but what I'm saying things in advance, is what we will see that although we will choose, let's say, this tilde to be 5 or 6 or something else, then the emergent space will be 3-dimensional.
Still.
Yes. So, of course, in the end, you want to take this C to be equal to 1. So you have one more extrapolation to do, but that is something that you have to do later.
There are 3 special ones of the matrices. There's 7, 8, and 9 are being chosen as special now because of your master.
They are going down.
Sorry?
They're suppressed by this.
So
they're not the ones that. Yeah.
Wouldn't it be more reasonable to leave those out of the XE? To choose it from one, the matrices from 1 to put an uppercut up and detail that. Choose it to be from 9 down to.
Yeah, this choice is partly motivated by SUSY deformation.
Yeah.
In that model, they also have the same structure. We introduce this psi term, then 7 and 9.
Yes, exactly.
In that case. So.
But that's why I would stay away from it with any artificial deformation. So that I can disentangle things a little bit more easily. Because I don't want to interfere with something that's.
Yeah, we can do that.
Yeah, we can do that. Yes, we have to try. So, as you know already remarked, this choice is motivated by a supersymmetric deformation that was proposed by Bonelli in 2002 to the matrix model. This includes one more term that we don't have at this point, Meyer's term here. And in case you add all those terms, then the action contains what we already have, plus the Meyer's term. And then you take all those deformation parameters, take those specific values, then this deformation is invariant under this supersymmetric transformation here. And notice that this part is the supersymmetric transformation of the original IKKT model, but you get an extra part here covered by this parameter mu. So you have only the one parameter deformation here, and this is something that we are currently investigating. So this is the model that we want to study here. We have the spatial permission matrices here, AI, I goes from 1 to 9, and we have the real variables here, tau, related to the time, and the action here has the bosonic term and the fermionic term of the IKKT model, plus the various deformations hidden here and there, and the gauge fixing action here. And this model here has a strong complex action problem. And in this work, we will address it by applying the complex Langevin method. So in order to apply the complex Langevin method, we have to complexify the variables. The taus are real, so we just let them now take complex values, whereas the AI are Hermitian matrices, and now they are led to be general S and C matrices. And the complex Langevin method is nothing but a coupled system of stochastic differential equations with a fictitious time. That sigma here represents this fictitious solution, has nothing to do with real time, where here is the drift that comes from the action of the model. That is the rate of change of the variables, and the stochasticity here is represented by this noise term, which is Gaussian, independent random variables for every sigma, and with the distribution here characterized with the 1/4. So there are many choices here, but what we will choose is we will take this noise term to be real, and this noise term here to be Hermitian. So, for example, here just showing for the spatial matrices, the solution to those equations is given by a probability distribution that gives us the distribution of the degrees of freedom at a specific time. And what is found is that as sigma becomes very large, then this probability becomes more or less independent of time. So in that sense, we say that the system here gets into equilibrium. And under certain conditions, there's a lot of things behind that, of course, it's just stating the final result. It is possible that if you take, let's say, an expectation value, so an observable here, degrees of freedom, then its average over the distribution given by the Langevin equations will be equal to the expectation values in the original system. And of course, in order for this to hold, there is a severe restriction here. Both the action and the observables, when they are complexified, must be holomorphic functions of the degrees of freedom. Then, after the system has reached equilibrium, after some equilibration time, sigma 0, we can compute estimators of the expectation values by considering the averages of the results of this evolution in the Langevin problems. Now, this method has some advantages, but it has also many disadvantages. The most serious one is the famous wrong convergence problem, where you see the simulation going as usual, but the end result is simply wrong. And that is why, from its original proposal by Rizzi and Lauder, I think, back in the 80s, not many people have used it. But there has been a lot of problems addressing the issues that make this method not work correctly, and it has been successful in many applications. Now, the problems may occur because there could be boundary terms when we do partial integrations in order to prove this central relation here. One has to do many partial integrations, so there are many boundary terms, and things have to fall off fast enough. There could be an influence of irrelevant subtle points in the complex plane, the singular drift problem, which I will explain, and some other problems that do not occur in our case, like large excursions in imaginary directions or integration cycles. But in our case, we have some confidence that it will work because we have already seen it producing results consistent in the case of the Euclidean model. So, of course, these equations have to be discretized to be put in a computer, and in our case, we apply a second-order Euclidean scheme that is quite quadratic and discretization errors in the time step delta sigma, and we take the time step to be 10 to the minus 5. Now let's go to the fermionic drift. That takes most of our computational effort. One has to compute this derivative here that involves the inverse of the operator M. So we have to compute this. And in order to do so, we follow a method that is commonly used in lattice QCD simulations. We estimate the value of this trace by considering auxiliary random variables chi that are white noise with this width here, this correlator here. And so in this ensemble, we take the average of this product here. Okay, so this is just independent random. So in this process, one has to calculate this vector zeta, which involves the inverse. And in order to do that, we use the conjugate gradient method to solve a linear system. And as Jun already pointed out, this is a huge matrix. It's dn squared. It's each size of it. So it increases both with the dimensionality as the square of the size of the matrix. And we also have to multiply here with entangler so that we have positive definite matrix to have the conjugate gradient method to work. Now, one thing that makes the calculation a little bit simpler is to realize that this matrix here is mostly zero at most of its points, and to use the actual action of the operator on the fermionic vector here that involves only n cubed order of magnitude operations to compute. So that is much faster than n to the 6. To avoid the wrong convergence problem, Nagata, Nishimura, and Shimasaki in 2016 proposed a very easy to apply criterion to make sure that this does not occur. And for that, one has to define a norm of the drift and follow its values as the simulation progresses. And all you have to do is to find their distribution, compute the histograms in practice in simulations, and show that they decay faster than exponential. So if you have parameters when they decay very fast, so you see faster than exponential decay, like say use e to the minus u square or something like that, then the simulation, you can have confidence that it produces correct results. But if you see these long tails that decay as a power law or something slower than exponential, then you might be worried that your results will be wrong. And of course, all the results that we will be presenting have been checked to satisfy this criterion. Another thing that we need to use is to use this stabilization parameter. This was introduced in lattice QCD simulations in 2019 by Atanasi and Jagger. It is not completely well justified, but it seems to produce correct results. In our case, we use it this way. We have this parameter eta. This parameter eta interpolates between the matrix A and its Hermitinization. So when eta is equal to 1, that's the Hermitian part of the matrix, and when it is 0, it's the matrix itself. And we put here a very small value, 0.005, just to stabilize the simulation. Another problem that we have found that occurs, and it will be discussed very thoroughly by the next two speakers, is that the non-compactness of Lorentz symmetry can introduce some numerical artifacts. And in our case, what we will do is, because the Lorentz boosts are the ones that are violent in the non-compact directions, we will use Lorentz boost to minimize this quantity here. This that has to do with the extension of time. And we just do a one parameter boost. Sorry for the notation. This sigma is not the time evolution of Lorentz of complex Langevin, the boost parameter here. So we take our matrices A0 and AI, we choose one direction here, not all 9, and we compute mu matrices here, and we repeat that with you can calculate when you take the minimum, and then you get A0 prime and A prime. And of course, A0 prime will not be diagonal anymore, so you have to rediagonalize here and obtain new times. And then you have to apply the same transformation to the other spatial matrices. So after we do that, we find that those numerical artifacts mostly disappear. Of course, what we are now trying to do is to actually apply a Faddeev-Popov procedure to do this case fixing in a more natural way, but that is work in progress. So you will hear much more about that in Nishimura's and Piensuk's talks. Now, what do we measure? That is the extent of time. You see, this is a function of time, t here. And for that, we use the trace A square of the little n by n matrices. We put a bar here to distinguish them from the big matrices here. And remember that now those matrices have been complexified and the expectation value will not necessarily be real. So the phase that comes here will give us information whether the dynamically arising space is real or not. So this angle here is something that we will measure. The other thing that we will measure is the moment of inertia tensor, but only for the little matrices representing the universe. So diagonalizing is not a holomorphic procedure. So we do a trick here, and for each configuration, we compute this determinant and compute those coefficients here, Ck, and we calculate their expectation value over the sample that we have, and then in the end solve this equation to give us the expectation values of the expectation value of the eigenvalues. And in order to compute statistical errors, we separate our data into bins, and we use the jackknife method to do so. So let me show you now some results. So for the results that I'm going to be showing, we start from a specially prepared three-dimensional bosonic configuration. If you don't do that, you will not get the same results that I'm going to be getting. So if you want to know what you get, ask me again. So the parameters of the results that I'm going to be showing is that we choose d tilde to be 5. So this Xi parameter that suppresses extra dimensions allows 5 dimensions to be large and makes the other ones artificially small. The size of the matrix is 128, gamma is equal to 4, and this suppressing parameter Xi is equal to 12. Our universe is a small 6 by 6 matrix. Okay, so the result here, we use the parameter MF, the fermion deformation term, to be the bosonic model here. Of course, we don't put any infinity, we just don't use the fermions. Then MF equal to 10 and MF equal to 6. So let me show you first the results for the bosonic model. So here on the right, on the left, you see the distribution of times. So you see the time here starts slightly has an imaginary part, and but then as we move to longer times, it tends to be parallel to the real axis, so the time intervals become real. And just in comparison here, this is the slope that one would get if one was obtaining Euclidean signature. So we obtain here Lorentzian signature at least 3 times. Now, what about the universe? The universe here, we adjust the time to be 0 in the middle. So you see the universe here starts being small. Okay, we ignore these are artificially suppressed. So then as the time progresses and becomes larger, the universe expands to larger values and eigenvalues of tensor. And you see this happens by preserving the SO5 symmetry. Now, if we include the fermions, put MF equal to 10, we get results that are quite similar. Again, we get this expansion here, real time. It's also real space, I'll show you later how this happens, but it's test, but also space and time are real in this case.
Real time because it is
Parallel to the real axis, and yeah, and the imaginary part is also quite small. It would be nice to know how they scale then, but that's all we have. But then if you further decrease, there is a value of MF which is close to 8, where we see a transition from this 5-dimensional expansion to an expansion that looks like this. So you see, we have the 5-dimensional universe here, and then there is a time, a very late time, where only 3 dimensions suddenly expand very fast.
how do you see D equal 5 and how do you see the dimensional state there? So it's 5-dimensional, then at some point transition.
So if you look at small times, it will look something like this, 5 and 6. The other ones are suppressed and 6. But here the scale is large. Then you see the
Only the upper.
go on.
Question, does the time also get a lot thinner? Does the time get a lot thinner?
No, it's more or less, it doesn't change.
No, the next one.
Huh?
You just have dots.
Here,
Yes.
yeah, we see some, we would like to have larger little system like this. But
Yeah, no, but the time is kind of the horizontal axis. There's a lot of points in the center, and it's very thin near the ends, right?
yes,
It's not quite uniform.
yes, we hope it's uniform.
Yeah, we only expect that to happen real times.
Yes.
At the beginning of this universe, there can be non-infinity.
So here for comparison, I put the two graphs for MF equal to 10, that I will be calling the bosonic phase. And here is where we hope that we actually see the effects of the fermions, giving rise to 3-dimensional universes at late times. Here I'm also showing you what happens at n equal to 96. These are some results that we have. Here MF is smaller, and here is 3.5. C is also larger, and we will see similar behavior. But we haven't seen that for smaller n. So large n may be important. Actually, think. So this is some data for MF equal to 4. Here I'm showing you also the 3-dimensional expansion. It's a little bit more noisy. It's harder to obtain data here. It takes longer. But I wanted to show you the behavior of theta s. If you look here at the horizontal axis is 0.00. So it is very small. So space is actually real. And in those plots, I'm showing you the block diagonal structure. Here you can see at the large times, it's quite thin. Now here I'm showing you here a rectangle. Different scale, you see it's more smooth, this block diagonal structure. Really, but as we go to longer times, it becomes thinner and thinner. So let's see how much time we have. 5 minutes. Okay, so I'll go through that very fast. I said that we use the Lorentz some boost transformations to get rid of some artifacts, and here I'm showing you one. If you take the bosonic model for those parameters here, you find real space and real time, but you also find this one dimension to expand along. So you might want to interpret this as a one-dimensional universe, right? But that is not so. That is an artifact of the Lorentz transformations. And in order to discover this, we defined the trace here of the matrices, and we see that we rotate them in the principal directions, so that we get the maximum traces. So we compute the trace here, And in order to get something that is not average to zero due to the symmetry, we fix the sign on one of the on the largest time here. So this pi here is the sign of this quantity here on the largest value of time. So what one sees is that the trace of all the matrices are very close to zero with an error, but then there is one matrix where the trace is almost linear in time. So that may be interpreted as a boost. And after we make this Lorentz fixing procedure, Lorentz symmetry fixing procedure, partially, of course, then this trace disappears. And you see here that not only the trace disappears, but also this one-dimensional expansion here also disappears, and we obtain the smooth nine-dimensional expansion here. There's no C. C is equal to 1.
This is much smaller X than you were using in the other cases.
Yeah, I mean, X equal 1. I mean, there's actually no C at all here. I just want to point out that we don't suppress anything. You see here, all 9 dimensions expand. Okay, so let me conclude. The Lorentzian IKKT model can be defined by a contour deformation from the Euclidean model. The two models are equivalent, and emergent spacetime is complex, Euclidean, and 3-dimensional. We introduced the Lorentz invariant master using a parameter gamma positive and defined the model in the limit where n is taken to infinity and then gamma needs to be taken to 0. We simulated the IKKT model using the CLM, including the smarts term, to avoid the complex action problem. To avoid the singular drift problem, we introduce a term which is quadratic in fermions, and the IKKT model must be obtained at the end by taking the deformation parameter to 0. Time is emerging dynamically. It is homogeneous, complex at small times, becoming real at larger times. And space is also real, mostly at all times, not only. We perform the Lorentz boost to remove the fact of the appearance of 1 plus 1 dimensional space-time. To increase the dynamical effect of the fermions, we perform the Lorentz invariant master using a parameter Xi, suppressing some bosonic matrices. And for d tilde equal to 5, n equal 96 or 128, gamma equal 4, we found that MF close to 8 separates two phases. One is the bosonic, where we have an SOD symmetric universe expanding, and one where SSB hopefully occurs. So what we're doing now is, of course, we want to make those results more firm by studying now larger matrices, expanding the parameter space. We're also trying to study the supersymmetric mass term, which is non-trivial. We have also to make many deformations to actually get close to the supersymmetric point. And also, we are actively using the Faddeev-Popov procedure to fix the Lorentz, partially fix the Lorentz symmetry to avoid numerical artifacts. Thank you.
So first of all, I'd like to thank the organizers for giving me this opportunity, particularly Denjo. And So I'm going to talk about this work done in collaboration with my students, Chen-Yu Cho and Ashutosh Tripathi and Jensen Wong. The last two papers are in preparation, but the first one is already published in PRL. So let me start with some brief introduction. I'm not going to repeat what Costa said, but one thing I would like to emphasize, in particular in my talk, is that this 2B matrix model or the IKKT matrix model is supposed to
include all the vacua in the string landscape as saddle points. And this is a very nice feature because otherwise, I mean, if we are just talking about perturbative string theory, you can never do that. But this model has the ability to do this. And that is precisely why this matrix model is so important to understand string theory. And you will see more why I say so, because we're going to see indeed a lot of saddle points in this model, and each of them describes the vacua of string theory. And another thing I would like to emphasize is that unlike the ADS-CFT, not only space but also time emerge from the matrices for the large n degrees of freedom. And this has not been yet achieved in the context of ADS-CFT, although we have some new developments in the context of holography and IKKT model, in fact, but that holography is still Euclidean. So we heard some nice talk by Sean Houghton last week, but let me remind you that even if we have some holography going on in IKKT model, what we have here at this moment is just time, just space emerging from the matrices, but not time yet. But now in this talk, I'm going to, well, also in Costa's talk, we are studying really time emerging from the matrices. That is something that I would like to emphasize. So let me first begin with some motivations for deforming a little bit this original IKKT action. And the reason is that if you look at the classical equational motions of the IKKT model, it looks like this. So as you see, in fact, the commuting configurations are the solutions to these equation motions, but there are no other non-trivial solutions. That has been proved, for instance, in the paper by Harold Steinacker in 2017. But so in order to have some more non-trivial solutions, is motivated to include the master. Can I have a laser? Yeah. Yeah, we include the master, which is Lorentz invariant. It looks like this. And this gamma is the parameter for the master. And once you do that, the equation motion will have this extra term coming from the master. And then there are many classical solutions which are not commuting ones. And in fact, commuting ones will not be classical solutions anymore. So it's only the non-commuting ones that solutions, but actually there are infinitely many of them. And in particular, yeah, one can find that, well, we have solved this equation motion numerically in this paper, and we have found that the extent of space as a function of time looks like this. So it typically has expanding behavior for gamma positive, but not for negative gamma. Unfortunately, as far as we do this classical analysis, we cannot determine the space-time dimensionality because arbitrary dimensionality is allowed as a classical solution. So in order to see really what is the dominant dimensionality, we have to do quantum calculations, but that was described by Kostas. So what we hope here is this one. So we hope that if you take the large n limit first, and then gamma zero limit from the positive side, and then we hope to see that 3 + 1 dimensional expanding spacetime remains in that limit. That is the hope. But and indeed, Kostas has shown us some numerical evidence that this can be the case. But since we had to introduce many deformation parameters due to the limitation of the computation method, it's not clear whether this is really true or not. And another thing I would like to point out, this was found quite recently, and we'll be discussing the next speakers. Next speaker, well, point is that the partition function for the Lorentzian model is actually divergent as it is. Even if you introduce this master, this is still divergent. And the problem comes from the non-trivial saddle points having flat directions due to the non-compact Lorentz symmetry. So if you try to integrate the flat direction along the flat directions, you always need to have the divergence coming from this partition function. So that happens. So we have to do something to cure this problem in order to define a model.
Sorry, and then I have a question to the previous slide. It's a very stupid question. What do you mean by a classical solution?
Okay.
You mean a solution with infinite matrices of that equation?
No, finite matrix. What I mean by classical solution is, in my talk, I always talk about finite matrices.
Finite matrix.
Yeah, so it's different from what you're doing in that sense.
So, but no, but I also know this equation with gamma very well. So I would expect that only one sign of gamma works, right?
Yeah, that is
the other one doesn't.
Exactly, that's very interesting point, and we will see that soon in the particular case of n equals 2, the matrix size E2. So, but here we have studied the solutions to this equation for large matrices like 120 meters. So that's 58, and we always find this expanding behavior. So this is quite generic behavior of the solutions of these equations. That is very interesting.
I give you the reference later with Armlin. He studied that equation.
Okay, that would be nice. Thank you. Okay. So I just mentioned that the Lorentzian model has the problem of function, so we have to do something. And there is actually a nice way to cure this problem, namely gauge fixing. And this is the main topic of the next figure. But anyway, the idea is to fix the Lorentz symmetry by using the Faddeev-Popov procedure. So as the gauge fixing condition, we choose this condition, which is to minimize trace A0 squared with respect to the Lorentz transformation. And then this is equivalent to imposing this condition for all spatial directions J. So we just introduce this condition in partition function using these delta functions. And then, of course, we have to include also the Faddeev-Popov determinant, which looks like this in this case of condition, where omega is just this 9 by 9 matrices in the case of original IKKT model. So yeah, this is a completely well-defined model in the sense that the partition function is now finite. So we study this Lorentzian model by computer simulations. And this is the first attempt in that direction. And then we also have this Euclidean version, but this is slightly different from the Euclidean model that Kostas discussed, because here we have as an integrand the phase factor instead of Boltzmann factor like exponential minus s. So we have this I in front of the action, and everything else is Euclidean. So SB, for instance, has the Euclidean signature and also the master. They are both SOD symmetric or SO10 symmetric. So this is different from what Kostas discussed as the Euclidean model, but we have I in front. And for the negative gamma case, we can make a Rick rotation or the phase rotation of the matrices. And then you can see that this model is kind of equivalent to Euclidean model that Kostas discussed. But here we are more interested in positive gamma regions. So in that region, we don't have any counterpart of the Euclidean model that Kostas discussed. Okay, so this is some subtle but will be important. And another remark is that in both of these models, you have these phase factors. I mean, in the Lorentzian case for obvious reasons, but also in the Euclidean version because of the way we define this model. So in order to be able to simulate these models, we need to do something with this oscillating phase because they induce the so-called side program or complex action program. And for that, we use the so-called Lefschetz thimble method that I'm going to discuss to some extent. Okay, so this is the plan of my talk. I will start to discuss the Lefschetz thimble method and also the Picard-Lefschetz theory, which are going to be very important in my talk. And then I will specify the model matrix size to n equals 2, which is the smallest possible matrix size that you can think of in this matrix model. But the good thing about this simplification is that you can exhaust all the classical solutions. So there's no ambiguity at all. So you know everything. As far as the classical solutions are concerned, you obtain everything that you want to need. What you want to know. And then I will show you some explicit Monte Carlo results for the Lorentzian and the Euclidean versions. And then if I have time, I also discuss the Euclidean SUSY deformed model that John Hartman discussed. But here we are going to study this model by Monte Carlo simulations for the matrix size 2 in particular. Okay, so that is the plan. So let me start with the method that we use. So suppose you have this kind of partition function where the integrand has this complex value action. Okay, and here for simplicity, I consider just x real variable and real variables x. So the original integration contour is along this real axis, but the idea of this method, well, of course, if you do the integration in this direction, then you have a sign problem because the integrand oscillates a lot. I mean, the phase oscillates a lot. And therefore, there is a huge cancellation among configurations that you generate by Monte Carlo simulation, and you cannot obtain any quantities reliably. But the idea of this method is to use the Cauchy's theorem that allows you to deform the integration contour in the complex plane like this. And we are going to deform it in a very particular way using this differential equation. So starting from some point on the real axis, we solve this differential equation using the derivative of the action. And then if you do this for finite flow time, let's say, tau, then the integration contour would look like this. And if you take the tau infinity limit, you will get something which we call Lefschetz thimble. That's the name of the method where it comes from. And in particular, this Lefschetz has to go through some point, which we call the saddle point, defined by this equation. And this is quite obvious because for such a point, the right-hand side of the flow equation will vanish. So this is always, these saddle points are always a fixed point of the flow equation. And so in the tau infinity limit, you always have a thimble which goes through some saddle point. And using this this differential equation, which we call the flow equation, you obtain a one-to-one map from the point on the original integration contour to a point on the deformed integration contour, and that defines the contour deformation. And the point is that due to Cauchy's theorem, the integration along this direction is the same as the one you would obtain on the deformed contour. And thanks to the property of this gradient flow, the sign problem becomes much milder on this deformed contour. And that can be understood in a very easy way. Just 3 lines. So the point is to calculate the derivative of action along the flow. So I take the sigma derivative. Sigma is the parameter that I introduced to define the flow here. So you take the derivative of action, and then by using the chain rule, you have to calculate this product. But this part is just nothing but, since this is the gradient flow that we use here, using that equation, you find that this can be replaced by this, right? This is the right-hand side. And then you notice that this just becomes some absolute value squared quantity, which is real positive, except at the saddle point, which makes this 0. Okay, so this means that the action, which is generally a complex valued function of z, the derivative of it becomes real positive, means that the real part of the action increases along the flow, whereas the imaginary part of the action is kept constant. And because of this property, you can easily convince yourself that the sign problem becomes milder along the deformed contour. And in particular, in the tau infinity limit, imaginary part of the action becomes just constant on this contour, which means that sign problem is in some sense completely solved. There's no fluctuation of the sign angle. Okay, so that is the idea of the Lefschetz symbol method. And yeah, the basic mathematical formulation of the Lefschetz symbol method is actually the Picard-Lefschetz theory, which corresponds to the tau infinity limit. And this is nothing but the multi-dimensional version of the steepest descent method. So in that limit, you have a bunch of saddle points that contribute to the integral because you obtain them at the thimbles according to this flow equation. So the original integration corresponds to just a summing over all the Lefschetz symbols that is associated with the what we call relevant saddle points that corresponds that can be obtained by the flow. But notice here that there are actually many more saddle points that are not obtained by the formation of the contour, and we call them irrelevant saddle points. Those saddle points, although they exist, will never contribute to the original integral. That is the very important point that has to be recalled later. But anyway, the bottom line is that an oscillating integral like this can be made totally well defined uniquely, and there is no ambiguity in the choice of integration contour. So, for instance, also when people talk about quantum gravity, a la Hartree-Hawking or Blenkin, there is a huge discussion about the choice of the integration contour. But now that we have this Picard-Lefschetz theory, this ambiguity is totally gone, and you can discuss quantum gravity as well in that direction. And I also have a paper on that topics with Jamie Cho, which you can take a look at. But anyway, let me move on to the matrix model, n+2 case. And here, let me start with the description of the classical solutions in this case. Okay. So this is the classical Gaussian motion after introducing the master. And for n+2, as I said, we can obtain all the real solutions up to the symmetry of the model. And for gamma negative, actually a mu equals to 0, the trivial solution is the only solution to this equation. On the other hand, if you look at positive gamma, you have two more solutions which are non-trivial. One is the so-called Pauli solutions, which has only A1, A2, A3, non-zero like this, which are proportional to the Pauli matrices. And there is also another one. This is what we call squash Pauli solutions. It has only A1 and A2 being non-zero, and they are proportional to sigma 1 and sigma 2. Of course, this is up to the symmetry, so you can generate many more solutions which are equivalent to these solutions. But the point I would like to emphasize here is that what about the symmetries? For the trivial solution, of course, all the symmetries remain unbroken. But the Pauli solutions breaks the original symmetry to this subgroup, diagonal subgroup of SO3, which is a part of the rotational symmetry, and SU2, which is this one. Okay, so you can think of the diagonal subgroup of SO3 cross SU2, and that remains for these Pauli solutions, but otherwise, I mean, all the other remaining part is broken.
Sorry, I don't remember whatever. But you're saying that even if you start with mu going from 0 to 10, you for n equals 2, you get only these solutions?
Yeah, indeed. Yes, because
there is no other solution.
No other solutions. Yeah, at least a real solution. Let me emphasize that. if you look at complex solution, in the next page I will
You mean
show you some.
permission or?
Real, I mean permission. Permission matrices are exhausted by all these cases, which is kind of interesting, and we can prove that mathematically. So yeah, is it okay? Similarly, for the squash-Pauli solution, the remaining symmetry is just SO2, which is the part of the rotation symmetry, plus U1, which is again the part of SU2 symmetry. Just the SU2 transformation generated by sigma 3 that makes this solution invariant if you make a appropriate two-dimensional rotation at the same time. That is what I mean by diagonal subgroup SO2 cross U1. But anyway, those are the remaining symmetries. In particular, these two solutions break the original symmetry, and therefore there is a flat direction, which makes the function divergent. And also, let me emphasize that these non-trivial solutions appear only for gamma positive, which is kind of reminiscent of the fact that we have only the expanding behavior only for positive gamma, but not for the negative gamma. So yeah, this nice, interesting behavior appears for positive gamma only, but not for negative gamma. So yeah, this shows that positive gamma and negative gamma are completely different, and we will see more from the numerical results later. But here, even at the classical level, you can see the difference between positive gamma and negative gamma.
Sorry, maybe a good question.
Yeah.
So I guess that equation that you were showing where you said SO3 is special, that one, for n equals 2. Now that equation is somewhat similar to the kinds of equations you get in fuzzy spheres, which exist for two-sphere and higher spheres. And for higher SOD, basically there's some constraint on the dimensions of the representations, which is probably why they won't show up on this small n.
Yeah, that's right.
So for the moment, you have no time at all.
Okay, so that's a very important point. The model has time. A0 is included. I mean, we have Lorentz symmetry. But if you look at the solutions, A0, we only have solutions with A0 equals 0. So in that sense, the time doesn't emerge dynamically in this n equals 2 model. But that will have a change if you go to slightly larger n, like n equals 3, 4, 5. Okay. For this very small n, the time doesn't emerge. That is kind of unfortunate, but yeah, we cannot. Oh, okay, so this is something related to what Ian's asked. So we actually have many complex solutions which can be obtained by kind of weak rotation. So for instance, even for negative gamma, if you think of these anti-Hermitian solutions, there exist such solutions. But the point is that those complex solutions are all irrelevant from the viewpoint of Picard theory. And in particular, we don't see them in simulations for obvious reasons. So yeah, even if such solutions exist, and the reason why they are irrelevant is very simple. The point is that all these solutions have real part of the action being 0, although the solutions are complex. And then, yeah, according to the Picard theory, as I already explained, the real part of the action should increase as you flow into the complex plane. So in order for these solutions to be relevant, it should have positive real action. The real part of the action has to be positive. However, they have exactly 0, as you can see immediately. So therefore, they cannot be relevant. That is the argument. And we can also try to do, by doing simulation, what we are doing is to deform the integration factor in the complex plane using the flow equation. And the fact that we don't see these solutions, these complex solutions, means that they are indeed irrelevant. Okay. Now, let me also mention what happens in the case of the gauge-fixed Lorentzian model. So far, we have been talking about ungauge-fixed model. But of course, in the gauge-fixed model, you have this gauge-fixing condition and also the Faddeev-Popov determinant. So the saddle point equation should be modified like this due to the Faddeev-Popov determinant. And well, at first sight, you might think that this is a bit complicated to solve, but in fact, using the SOD symmetry, which is still remaining, we can impose a further condition like this to using this symmetry, and then the equation simplifies like this. So actually, the term coming from the Faddeev-Popov determinant looks like additional master with some index mu. So k mu is defined in this way. So this equation has to be solved with this equation in a self-consistent manner, but that can be done by using some ansatz. And yeah, you can do that. Okay, and one thing I would like to emphasize at this point is that since the Faddeev-Popov determinant induces this extra mass-like term, even for gamma equals to 0, the commuting saddle points will not be the solutions anymore at gamma equals to 0. So yeah, it has a kind of very important effect. Okay, so in order to solve the saddle point equation for the gauge-fixed model, we have to use some ansatz. And in fact, without loss of generality, we can assume that a mu has this form. So here we have to introduce some non-zero A0. And the reason for this is kind of very interesting because if you have A0 equals to 0, in fact, the Faddeev-Popov determinant becomes 0. And then it obviously there is no solutions. So in order to avoid having this Faddeev-Popov determinant being 0, we have to assume that A0 is non-zero. And without loss of generality, we can just assume this form, this sigma 1, sigma 2, sigma 3 being power by matrices. Okay, then for positive gamma, we obtain these solutions. Sorry. In the large gamma limit, yes, if we take the large gamma limit, then of course this Faddeev-Popov term will be negligible compared to the others. So yes.
There's one small thing that I don't understand. The A0 is different from the others because of the metric in the equation. So
Yes.
in that equation, you always have Lorentz metric.
Yes.
Okay. So what I don't understand is why in that solution then A0 is sigma 1 because why is that special? I mean, sigma 1 and sigma 3 are real. Sigma 2 is complex.
Sorry.
So I don't understand why A0 is sigma 1.
Okay. First of all, real or complex is not important. Permission or not permission is important.
Yes.
So in that sense, sigma 1, sigma 2, sigma 3 doesn't really matter. And you can choose whatever Pauli matrix you want.
But
A0.
in that sense, A1, A1, the thing you wrote down,
Yes.
A0, A1, A2 are treated democratically. But I would expect A0 to be singled out because of the metric. That's what I don't know.
This is just an answer, so you will find that X and Y and Z are quite different.
Okay.
Just three Hermitian 2x2 matrices is equivalent to three vectors in R3. The three you've chosen are perpendicular. Is there some reason for choosing the perpendicular?
Yeah, by using the symmetry. Yeah.
Sorry?
By using the symmetry of the original model,
you can make the perpendicular.
Yeah, make them.
Matrix.
Yeah. So we make a full use of the symmetry, right? You see that you can always assume that the solution can have this form. Yeah, but this of course requires some explanations, which I'm going to skip right now. But anyway, I want to emphasize that in the large gamma limit, the solutions for this gauge-fixed model should converge to those of the ungauge-fixed model. And for the ungauge fixed model, we know already that these are the solutions. So we are going to search for, so X, Y, and Z can be complex. Now that we have introduced the gauge fixing, there's no reason to assume that they are only Parisian solutions. So we have to solve this equation for arbitrary X, Y, and Z complex values. But the point is that in the large gamma limit, the solution should converge to one of these solutions. And that is the criterion for picking up the relevant solutions from this solution, from this equation. Okay. So, and then the bottom line is that since, if you do that, we find that you can never have a Pauli solutions because A0 has to be non-zero. At this point, I had to assume that A0 should be non-zero, so that's why we have to use sigma 1 here. But then we cannot have we cannot have three spatial directions to have non-zero large gamma limit. So the only relevant solutions that we obtain in the gauge fixed model is those which converge to the squashed Pauli solutions, as is obvious from this assumption, but not the Pauli solutions. There's no relevant solutions that converge to the Pauli solutions at large gamma. So this is a very interesting effect of the Faddeev-Popov determinant. Okay, so now let me show some numerical results for the Lorentzian and Euclidean versions of the N=2 IKKT model. So first, let me show the results for the Lorentzian model with gauge fixed Lorentz symmetry. And here we plot the real part of the trace of AU, which is a Lorentz invariant quantity. And the x-axis is basically just gamma, the mass term that we introduced. And as I said, negative gamma region and positive gamma region are very different. In the negative gamma region, it's more trivial because we only expect that trivial saddle point is going to dominate the region. So all the non-zero results are just due to the quantum fluctuations. Basically, this is zero at the classical level. On the other hand, if you go to the positive gamma region, you have a linearly increasing behavior, which is due to the squashed Pauli solution dominating the large gamma. And this is the only saddle point that dominates in this gauge fixed Lorentzian model, positive gamma region. And another thing is that if you look at the region close to the origin, the data points just smoothly changes. So there's nothing very similar happening at gamma is 0. Okay, and if you regularize the Lorentzian model by a cutoff, which is discussed by the next speaker, in fact, you obtain thimbles associated with Pauli saddle point as well. Not only the squashed Pauli, but also the Pauli saddle point. So indeed, the gauge fixing has a very important effect. Even the saddle point changes. The number of saddle points, relevant saddle points changes. Okay. Then let me also show you some results from the Euclidean model. By Euclidean model, I mean this model, which is obtained by just replacing A0 with I times AD in the Lorentzian model. That's it. And then in this case, we don't have to gauge fix, so just this model. And here we plot the same thing, but the real part and the imaginary part separately, as a function of gamma, basically, this last term. And it looks quite similar in the negative gamma region. And the reason is, again, trivial saddle point is the only saddle point in this region. But the difference is in the positive gamma region. Now, the red data points represent the Euclidean model results. You see a very interesting oscillating behavior for the real part and the imaginary part, both of them. What are they? In particular, the results are different from the gauge-fixed Lorentzian model, which is shown by this black data. See, so from these results, we can safely conclude that the Lorentzian model, which has Lorentz symmetry, gauge fixed, and the Euclidean model, they are not equivalent to each other. Now, what is this oscillation? Before I talk about that, let me first explain this interesting behavior at the origin. You see, for the Euclidean model, we have a sharp peak at gamma equals to 0. And this is actually due to the commuting solutions dominating exactly at gamma equals to 0 only. For the gauge-fixed Lorentzian model, as I explained, commuting saddle points are not solutions to the equation of motion anymore. So you don't have this peak. And you can also confirm that by looking at some quantity that represent the non-commutativity of configurations. This is commutator squared, basically. And for the Euclidean model, this quantity drops down very sharply at gamma equals to 0, which, of course, suggests that commuting saddle points indeed emerge in this model, Euclidean model. But that doesn't happen in the Lorentzian model. It just goes up on the positive side for the reason we don't really understand. But the point is that it doesn't go down at gamma equals to 0. So this shows that commuting saddle points emerge only in the Euclidean model at gamma equals to 0. Now, let me just quickly explain what is the oscillating behavior seen in the Euclidean model at positive gamma region. This is in fact due to the kind of interference between the squashed Pauli solution and the Pauli solutions. Let me remind you that in the Lorentzian gauge-fixed model, we don't have Pauli solutions, so there is no chance to have such a interference or oscillating behavior, which is consistent with what we obtained for the Lorentzian model. But now in this Euclidean model, since Pauli can be also the saddle point, and these two saddle points actually, you can calculate the partition functions around these two saddle points using productive calculations. And if you look at that, for d equals 5, exactly at d equals 5, these two partition functions has the same power of gamma. So if we plug in d equals 5 here and here, you find that it is 3/2 for both Pauli and squash Pauli. So that means that for exactly d equals 5, you have both saddle points contributing almost equally. And now, if you look at the gamma dependence, you have also this phase factor, which has different coefficient. So because of this difference of the phase factor, when you sum up the contributions from these two saddle points, you can have some interference. So you can have an in-phase or out-of-phase contributions from these two saddle points, and that result in this very interesting oscillating behavior. And let me also emphasize that this can be seen only in the system with the complex action with the sign problem. If you don't have such phase factors in the partition function, if it's just boson weight, such oscillation will never happen. So this is kind of a very successful result for our method. Okay, and if you go to larger D, what happens is that this Pauli solution will dominate more than the squash Pauli because we have a larger power of gamma. And therefore, so this you can see by red and black circles like this. So as you go to larger and larger D, this oscillation is kind of becomes weaker. And this black line here is the result obtained by 1/d expansion, which will be discussed by next speaker in detail. So we approach this smooth curve in the large D limit. So so this is what is going on in the Euclidean model. So let me emphasize that you have two saddle points indeed contributing in the model, whereas in the Lorentzian model, it's only squash Pauli. Okay, so that's it for the comparison of the Lorentzian model and the Euclidean model. And for the remaining time, I'd like to discuss some more results that obtained quite recently with students. And yeah, this is about the SUSY deformed model that Sean Huck discussed last week. So this is the original IKKT action, and we first make a weak rotation to the Euclidean model by this replacement of A0 by A10. And then on top of that, we introduce some term S omega to the action, which actually preserves 16 supersymmetry of the original model. So you have this mass term, which is different for 3 directions and the remaining 7 directions. And you also have the Myers term, the cubic term for the 3 directions, and also the fermionic mass term for the 1 to 3 directions. So this is the particular deformation that preserves 16 supersymmetry, which is analogous to the BMN model, BFSS model. And this model has attracted large, big attention recently, basically last fall, since they have found the holographic duo of this model. This is very new to the IKKT. For many years, we didn't have a holographic duo of the type 2B matrix model, but now suddenly people have discovered it. And another interesting thing about this model is that you can solve it by using the SUSY localization technique. This was done in this paper, and the end result is this. So the partition function for this SUSY deformed model can be written this way, in a very simple way. And Hartnell and Liu took this as the definition of the partition function, and they calculated it using Monte Carlo technique directly to this localization result. And this model does not have any sign problem or anything, any problems. You can do it very easily. And they went up to n equals 40, and found an interesting phase transition at some omega. There is a sharp first order phase transition in this model. But there's a kind of subtlety when you try to take the omega 0 limit. Naively, you might think that omega 0 limit will give you back the IKKT model, but that doesn't seem to happen. There seems to be some singularity, and in particular, this partition function in fact diverges in the omega 0 limit, whereas for the original IKKT model, we know that the partition function should be finite. So there is something strange going on in this limit. So the purpose of our work is to clarify what is going on in this limit, SUSY deformed model. And that you can also study by Monte Carlo simulation. And in fact, let me first mention that this model does not have a sign problem for n equals 2 case, because the fermionic term, after you integrate the fermions, you get real positive Pachian. So there's no sign problem whatsoever. So you can study this model by standard hybrid Monte Carlo method without worrying about sign problem. But the real problem of studying this model is that there are actually 2 saddle points contributing to this system. So you have to be able to sample both of these saddle points with the correct weight. And that is not so easy. But there is a standard technique called the parallel tempering method, which is quite often used in UCD simulations, for instance. So we did it, and we were able to find the 2 solutions, 2 saddle points. So let me first show some comparison with the localization result. So the localization result is very nice, but the problem is that you can only calculate some expectation values of operators which preserves supersymmetry. So you cannot. There are many observables for operators that you cannot really access by this method. But there is one nice quantity which is not just the derivative of S omega with respect to omega, which is calculable by the localization technique. The result is just blue line, and as I said, omega zero limit is singular, and indeed this quantity goes to negative infinity. That is the sign of the singularity. But our numerical data agrees very well with this prediction by the local equation. So this confirms that, well, our method is doing well, and also the local equation result seems to be correct. And now we would like to talk about n equals 2 once again, because in that case we can find all the saddle points. And here we use this ansatz, similar to what we used in the previous section. So you have these Pauli matrices with some arbitrary constants, and then the action takes this form as function A, B, and C. And in particular, this comes from the Pappian. So here I'm talking about the saddle point equation, including the Pappian. Okay. And for the omega zero case, which is nothing but the original Euclidean IKKT, n equals 2, bosonic, the solutions can be found like this. So A, B, and C turns out to be equal actually for the saddle point, and it takes this particular value. And now, inspired by this result, for omega non-zero case, we also assume that A, B, and C are equal. Then we can easily solve this equation and find these solutions, which goes to the IKKT result, this value. And for the large omega, in the large omega region, it approaches this quantity, which is proportional to omega. And this can be understood because at large omega, the classical configuration dominates, and we know that in this case we have a fuzzy sphere. So that is what is described here. Fuzzy sphere dominates at large omega. Okay, but yeah, now about the singularity that appears at omega equals to 0. This solution does not explain anything about the singularity. In fact, if you just look at this solution, you find that omega zero limit agrees with the original IKKT model. So well, you cannot explain anything about the singularity. But the solutions that is relevant to understand the singularity is actually this one. So in fact, we notice that there is a very simple solutions which looks like this, having only one of the remaining. Well, this doesn't have to be A10, but it can be also A4 or A5. But anyway, by using symmetry, we can assume that A10 is non-zero, and on top of that, we can assume that this is Pauli matrix. So we choose sigma 3. It doesn't have to be sigma 3 again. But anyway, so if you have this ansatz, then you find that the action looks like this, and then taking the derivative, you get this this saddle point equation, and which has 3 solutions. But of course, x equals 0 is just a trivial solution, which is not interesting. And so we look at this solution, and yeah. So first of all, it diverges indeed at small omega like this. Yeah, obviously, diverges like this. And another interesting thing is that if you go to larger omega, at some point this solution ceases to exist exactly at this point. So yeah, this solution exists only in this region, and it diverges towards the origin. So and this saddle point is indeed responsible for the singularity that people have been discussing. Okay, now yeah. Okay, so here I show some. Yes, 5 minutes. Yes, thank you. Some results, which are inaccessible like by localization. So first, we consider trace I squared with I sum over 1, 2, 3, and the data points we obtain are these data points, and the blue line corresponds to the saddle point that I discussed at the beginning. Okay, so our result indeed agrees with the saddle point at large omega, which is the Pauli saddle or fuzzy sphere. But then at small omega, our data points actually increases, but this cannot be understood by the saddle point. This is just a kind of quantum fluctuations. If you look at the remaining directions, like we trace a squared from 4 to 10, our data points actually becomes very small, large omega, which is kind of in agreement with the commuting saddle point that I discussed here. This one shows that this quantity should be quite small, and sorry, I'm very sorry. At large omega, we expect that our data points corresponds to the fuzzy sphere solutions, but for the fuzzy sphere solutions, only A1, A2, A3 are non-zero, and the remaining is 0. So here it is natural to see that our data points are very small. On the other hand, if you go to small omega, our data points start to increase, and this is qualitatively consistent with the behavior of the commuting saddle points, namely this saddle point. But of course, there is some discrepancy due to some quantum fluctuations. So our data points are indeed suggesting that at large omega, we have this this fuzzy sphere solution, but at small omega, the commuting saddle points are the ones that are dominating. And we can also see that by looking at the action. So the blue line is the action for the fuzzy sphere, and the red line is the action for the commuting saddle points. Then indeed at small omega, commuting saddle points have smaller action, but large omega, blue fuzzy spheres has smaller action. So it is natural that in this region, commuting saddle point dominates, and this region fuzzy sphere dominates. But there is some crossing point here around omega equals to 4. So we focused on this intermediate region of omega. And
before you leave that, yes, just wonder why you're describing the fuzzy sphere saddle as that small omega as huge quantum fluctuations. Shouldn't they really just agree with the commuting saddle?
Exactly, yeah.
Then you could.
Sorry. So, yeah, in this region, we expect that our configuration is dominated by the commuting saddle for sure. But for the commuting saddle, this is very small.
But you have 2 points here, which
is very
presumably have the same expectation value if you divide by 1/3 and 1/7 or something, that they're more or less the same. The two that you've circled should agree more or less with the commuting saddle.
Yeah, but if you look at the commuting saddle point, all the
but you're doing a numerical simulation, so it doesn't really know about which side you're doing.
Oh, yes, but yeah, basically, this is just a saddle point. So in simulations, we also have quantum fluctuations, another saddle point. I think quantum fluctuation is really responsible for this discrepancy. So
you're saying that you don't get an agreement with the other saddle, with the commuting saddle.
I mean,
from the point your simulations.
Yeah, the red line is the one that is predicted by the saddle point analysis, but our data disagrees with them. But this is just the quantum fluctuation. I mean, at large omega, of course, quantum fluctuation is suppressed, but at small omega, it's not no longer suppressed. So,
but you should be able to jump into the commuting saddle. You should fluctuate into the commuting saddle. And so the distinction between 1 to 3 and 4 to 10 should disappear. And it looks like it does to me. But anyway, let's discuss it afterwards.
Yeah, okay. yeah, in the omega zero limit, the rotational symmetry doesn't restore actually. We can also check that. So it doesn't be the same between these two. Yeah, so anyway, in the intermediate region, we do see two peak structure in the history of histogram of these quantities. And the two peaks indeed correspond to the meeting saddles and fuzzy sphere saddles. And as we change omega from 3 to 5, the higher peak kind of switches. Okay, so since I ran out of my time, let me summarize quickly. So we have seen the emergence of various saddle points in n=2 IKKT model. And we were able to do that by using the Lefschetz method to overcome the sign problem. And this is indeed a kind of a prototype of a string landscape. And of course, if you increase n, there will be infinitely many more saddle points, but this is just a prototype. And also, we emphasize that the Euclidean model and the Lorentzian model are indeed equivalent, even if you preserve the Lorentz symmetry by using a procedure. And in the Euclidean model, we have seen a very interesting interference between Paulinians plus Paulus positive comparison, and also the emergence of commuting saddle points in atom of gamma equals 0, again in the Euclidean model. And we also studied the SUSY deformation in the Euclidean model, and confirmed that there is a different vacuum or the diverging commuting saddle in omega 0 limit. So all these questions are related to the important question of what is really the correct definition of the IKKT model. For sure, we should use the Lorentzian, but what kind of deformation, whether we should use gamma or omega, we don't know. So that is very interesting question we still have to address. So so we haven't studied yet the Lorentzian SUSY deform model, so this is one interesting direction. And also the Lorentzian SUSY model plus the gamma term, we've been doing using complex Langevin at large n, but we can also try to do that by using the Lefschetz method. The big advantage of Lefschetz method is that we are able to sample all the relevant saddle points by one single simulation. Whereas in the complex Langevin method, if you prepare the initial confusion carefully, then you can try to see one saddle point, but you never know whether it is relevant or not. We can only discuss the stability of the saddle point. So I think it's important to also do Lefschetz simulations. And the property of token has been discussed by also, so I can read. Unfortunately, the cost of Lefschetz method is much higher than the complex Langevin method. It grows typically in like 10 to the 6 for large n. So I hope we can do n equals up to 16 or something like that, but 100 or 1000 is out of question, I'm afraid. So, but anyway, we still have some hope that we can. Thank you very much.
Thank you very much, organizers, for inviting me to give a talk in this wonderful workshop today, and congratulations on your DIAS anniversary. So in this work, I'll be presenting the work that we have done with Yuma Sano, Jun Nishimura, and Naoyuki Yamamori. So it will be based on the two papers. So the first one we have already published. This one we discussed more about the toy model, which we use to kind of illustrate some of the properties that appear in the IKKT model in a more simple way. And then there is another paper that we're writing right now, which will be wholly on the IKKT model. We hope to publish it within this day. Oh, you cannot hear me?
It's okay, but it'd be nice.
I like this one. Okay. You can hear me clearly.
Yes. Yes, I can hear you.
Okay, thank you. Great. Okay. So I don't think I have to give the introduction anymore, but let me just go through this quickly because there's some point I would like to mention. So of course, the IKKT model was proposed by these 4 Japanese gentlemen as a non-productive formulation for superstring theory. The model was defined by this Poisson function, where you have the action composed of the bosonic and thermic degrees of freedom. And the matrix degrees of freedom, the number of them depends on the dimensionality D. And the original proposal was at D equal 10. But here, later on in this talk, I will focus more on the bosonic model, which we don't have the restriction on the dimensionality from the supersymmetry. So the D will, can be arbitrary. And this will have an effect on our ability to do some non-productive calculation analytically. Yeah, and one of the most important features of this model is that you have this kind of shift symmetry, but it can be identified as a translation in supersymmetry algebra. And therefore, you can interpret the eigenvalues of the bosonic matrices at the spacetime coordinates, and therefore the spacetime emerges dynamically from the model without assuming it in the first place. Right. Kostas has already introduced you to this property of the Lorentzian model. But so essentially in this work, they found that if you do a weak rotation like this, you can relate this kind of quantity that we compute in the Lorentzian model with the one that we compute in the Euclidean model with some phase factor here, complex one. And therefore, this means that the emergent spacetime in the Lorentzian model is actually Euclidean and complex, which is not very physical. So they introduced the mass term given by this expression, and therefore using the same weak rotation as Jun Nishimura has already talked about it, that you pick up some complex phase factor in the mass term, and therefore when you consider a gamma, a negative gamma, you find that the real part of this weak rotated mass term is actually positive, and therefore with the minus sign here, it becomes finite, and then you can make a connection to the Euclidean model. However, the things are completely different when you consider the positive gamma, where the real part is on the opposite side, it's negative now, and the whole thing is unbounded, and therefore you cannot really connect it to the Euclidean model anymore. So the important thing is that we'll be focusing more on the positive gamma side, essentially. Yeah, one thing that is very important that hasn't been discussed too much yet today in the 2 talks before is that the Lorentzian model is not absolutely convergent. This one we already know, because even though we integrated out the Fermi degrees of freedom, we still have, and we get the real polynomial Haffian, we still have the purely oscillating phase from the bosonic part and the mass term. So in order to make it convergent, you need to introduce a convergence factor, which here we characterize it by epsilon. And then if you expand at a small epsilon, you get this kind of term. And therefore, the Poisson function contains this kind of exponent here. And so you can see that here we have the combination of epsilon and gamma. So therefore, this whole Poisson function is absolutely convergent for when epsilon and gamma is of the same sign. But of course, we will be focusing more on this part. Yeah, and the other thing is that, as you can see from the combination here, that this breaks the Lorentz symmetry. So therefore, we call the epsilon is kind of like a Lorentz breaking cutoff. Yeah, so the question you can ask is whether we can recover this Lorentz symmetry in the limit of epsilon going to 0.
Sorry, I missed why you introduced epsilon?
To make it absolutely convergent, because here we have the I here, and with the I here, so we can have some decaying factor. Yeah, and so this question of whether we can recover the Lorentz symmetry or not is will be kind of discussed, but essentially we cannot, because there will be some artifacts from the Lorentz symmetry, as Jun Nishimura has already give us some hint in his presentation. But here I'll talk about these kind of artifacts in a more detailed explanation. So essentially, the result that we found as a short message before we go on into more details is that we first derived all the classical solution in the bosonic model with the mass term, of course, at n equal 2. So this is a metric size. And the thing that we found, we have two important results. The first one is that the Poisson function, out of all these classical solutions, there are some of the solution that breaks the Lorentz symmetry, so you have kind of like a flat direction. But because the Lorentz symmetry is non-compact, so we found that the Poisson functions around those kind of solutions are actually divergent because of these non-compact vibration. And the second result that we found is a very interesting one, is that with the presence of the Lorentz breaking cutoff, we found that it's actually restricting the quantum fluctuations. And this kind of restriction remains even after we remove the Lorentz breaking cutoff by taking this limit. Therefore, we call it the cutoff artifact. And yeah, I'll show this in a minute, or not in a minute, but okay. So the outline of this talk is that I have already given you the brief review of what we're going to do and what is the IKKT model. And now I told you that we're going to study, we're going to show what are the artifacts that appear in the IKKT model. But before that, we talk about the toy model first, which is simpler. And then we'll go on to the IKKT model, discussing the classical solutions and also what is called the one-over-D expansion. So the D here, I remind you that this is the number of bosonic matrices. So this is a kind of tool that we can use to do the non-reductive analytic calculation in the mass term. Yeah. And then we'll talk about what are the artifacts that appear in the IKKT model, kind of related in resemblance of the what appear in the toy model. And then we'll propose the new definition of the IKKT model by gauge fixing the Lorentz symmetry. Then we'll summarize the talk. Great. Yeah, so first we'll talk about the toy model and what are the artifacts that appear from it. So yeah, if I speak too quickly, and just stop me. So essentially, in the bosonic IKKT model, which we'll be mainly focusing on this work, it is a series of n square minus 1 Lorentz vector, and you can see this by expanding the bosonic matrices using the SUN generators. So this kind of index A is what we meant by Lorentz vectors. Yeah. So in order to make things simpler, we consider a toy model of just one Lorentz vector, of course with the Lorentz symmetry, defined by this Poisson function. So x mu here is to represent a kind of this real variable here, right? So one thing is that you can solve with this model, you have this kind of classical equation in motion. Just take the derivative of this exponent. And at the positive gamma, we found that there is classical solutions. There are two types of them. The first one is what we call the trivial solution. It's just this part. So this represents one single saddle. However, there is another type, which is represented by this equation. And this is a family of infinitely many saddle points. It's coming from this part. Yeah. And so,
Summation.
Oh yeah, sorry. Right. Thank you. Yeah. Okay, cool. So then we introduce, to make things similar to what we have in the IKKT model, I introduced the Lorentz breaking cutoff in a similar way as well by this one. Right. So now I talk about the 1/D expansion, what it is, but here I will give you like a kind of a glimpse of what it is to be able to calculate things non-perturbatively. Because if we consider just the classical solution, with the factor of gamma here, we can do, usually we can just do perturbative calculation around these kind of classical solution in 1 over gamma. But here I will talk about how to do things non-perturbatively in this 1 over gamma factor.
First question.
Yes.
Is your gamma imaginary or?
Real.
Yeah.
Yes.
Well, that's a very bad interval.
Yes.
Yeah, we try to simplify things a little bit so that we don't have like a sign problem or whatever to care about too much. But yeah.
Well, the alternative would be some kind of dividing by the Lorentz symmetry, but using some Faddeev-Popov. So should that give the same result?
Oh, you mean, yeah, okay. So if we do the Faddeev-Popov procedure, then we'll have what we call the gauge fixed model. And that is the end of this section, actually. But so if I can come back to that. Yeah. Okay, great. So we start from here. And what we do next is we use the Hopper-Stratonovich transformation to introduce the auxiliary variable k, so that the action can be rewrite into this form. And so what you can do is you can complete the square, make a shift in the variable k, and then you can integrate it out k to get the original model back. But now what we proceed on is that we do some arithmetic rearrangement of variables. So we separate x mu into x0 and xi to make things more clear. And then rearrange it into this way, which you can see now that it becomes some kind of Gaussian integral. So you can integrate it out x clearly from here, and then you get this Poisson function defined in terms of variable k. And the effective action here is given by this expression. So this is what we're going to be working on. Yeah. Right. Okay. So the effective action is defined by here. Now you can do what you can do is you can study the saddle point by solving this saddle point equation. You can clearly see that because this factor and this factor is different, and you have k here, so this is a cubic equation. You have generally 3 solutions. And what we do now is we pick one of them, a very interesting one. So this is one of the saddle that of this equation. Its leading order is order epsilon, not order 1. So what we found is that if we substitute this k north, this saddle, into the Poisson function, so it's just a saddle point contribution. What we found is that the Poisson function actually diverges as you set epsilon to 0. So in order to understand how is this divergence come up, we go back to this this equation, this Poisson function. So from here we can deduce that the expectation value of k is related to that of the x mu by this kind of relation. And okay, and what we can do is that we consider epsilon going we consider epsilon equals 0, and we compute this expectation value just using the saddle point contribution. So substituting k equal k north, this k north here into this one. So at epsilon going to 0, because it's proportional, the leading order is proportional to epsilon, so you get 0. And now this is the same as if you compute this equation. I omit these kind of factor, it's not related. So if you compute this kind of quantity at the classical contribution, you get also 0. So what this means is that the k north saddle is corresponding to this kind of saddle point that where we have infinitely many of them that are living in the same family. So yeah, and just let me give some remark on what is going on with the other saddle that we ignored. So one of the remaining saddle correspond to the trivial solutions, and the other one so the other one is irrelevant according to the Picard-Lefschetz theory. Of course, we haven't done explicitly showing that that one is really irrelevant, but we believe so. Yeah, and yeah, well, the Picard-Lefschetz theory has already been introduced in Jun Nishimura's talk, but I will just give you quite a quick one. So essentially what we have is suppose we have originally the integral, the Poisson function on the real line, and the action is complex. So you have some oscillating weight. So it's not well defined, especially in numeric simulation. So what you can do is you first analytically continue to a complex plane, denoted by Z here. And what you do next is you deform the contour according to the holomorphic gradient flow defined by this equation, and the flow is tau. The flow time, the fictitious one, is tau. So what you can prove is that the action along the flow is actually positive semi-definite. So the imaginary part is constant. And this is what solves the problem of the sign problem, the oscillating weight. But the important thing that I would like to discuss about that is related to this talk is that we have the concept of irrelevance or relevance saddle. And what we can do to determine their relevance is that we see whether there is some kind of flow from some point on the real line, the original contour, to the saddle point. If there is a point flowing to the saddle point, then we call it a relevant saddle. If there is no such flow, then it's not relevant. And this is what we meant by this notion here. Yeah. So now we come back to trying to understand the divergence of the Poisson function. Okay. So let's look at this picture, right? Okay. So I conjecture here that is coming from this. Well, we show that there is a correspondence between the saddle point K north to this kind of solution, and this kind of solution can be represented as a green curve here in the configuration space. So it's kind of non-compact.
So what would happen
yes.
in the Euclidean case?
Sorry?
The Euclidean.
In Euclidean case, this is not non-compact, so it's kind of like a circle, if you may.
So wouldn't that be a way of regulating the integral?
The divergence will not. There will be no divergence.
Right. So if I try to analytically continue from the Euclidean case, when I get this epsilon prescription, or it's completely.
Okay. First of all, it's not quite relevant here, but not sure. Maybe there is some issue with the sign of the gamma in front. But yeah, but we're not trying to make some connection with the Euclidean model. Okay. But thank you for the question. So okay, so along this green curve, there are infinitely many saddles that are related to each other by Lorentz transformation, which you can clearly see from the expression here. So this means that when you compute the Poisson function around this kind of saddle, this means that you're summing over all these infinitely many saddle points. So what you get is that the Poisson function will be proportional to the volume of the Lorentz group, which is non-compact. So that's why you get divergence. So essentially, the take-home message is that the divergence comes from the non-compactness of Lorentz symmetry. Hope that's clear. And another thing that I have already introduced a little bit before we get into the detail is that there will be some kind of restriction on the quantum fluctuation. And we can show that by expanding the K around K north.
Just to go back, in your original, I mean, if I take your Hubert-Stratanovich version of the model,
right?
Isn't it clear already that you have an infinity from the Lorentz invariance? Because I can do any Lorentz transformation on the x's in that. Right. So the measure that you're integrating over x there, dx.
Okay.
That's already divergent.
It's not so clear. I mean, if you're only looking at one saddle, this one.
Well, you've written the integral here. You have an integral dk and dx. That dx integral, well, there are an infinite number of I can do a Lorentz transformation on the variable there, and I get the same integral.
Okay.
So there's already divergence there.
Well,
Yeah, but not when epsilon is different than 0.
100 epsilon is different.
So an epsilon equals 0, right?
Yes.
An epsilon different than 0.
Right, sorry.
So, yes.
Okay, good.
So this is, right.
okay. So we're now expanding K around K north. Remind you again that this is what it is. And so now the effective action written in terms of the fluctuation can be written like this. So what you can see here is that delta K always appear with a factor 1 over epsilon. Here and here, apart from the saddle point contribution. So what you can deduct from here is that the fluctuation scale as epsilon. And therefore, when you compute the observable K, the expression value of K like this, so you have the saddle point, which is order epsilon, and the fluctuation, which is also order epsilon. And so the whole thing is also of order epsilon. And now you have this relation, which means that from here, this part is epsilon, so you can move this one to here. And what you get is that in the limit of epsilon going to 0, this quantity is actually just equal to -1. And this is exactly just the classical contribution. So we call this kind of phenomenon the classicalization. So in order to understand how the fluctuation, how the restriction of the fluctuation appear, we look at the mechanism that we would like to present here. So of course we start with this Poisson function with the exponentially decaying cutoff, but we would like, and we have the same picture here that we introduced before, but now we would like to simplify the situation a little bit by introducing the sharp cutoff defined by this equation here. And so you can think of this gamma lambda as 1 over epsilon. So here we put this kind of cutoff, or we call it cutoff surface, the spherical one, at one of the saddle point. We call it a boosted saddle point along this green curve. And so now the question is, what happened to the fluctuation here along these saddle point? So what we can see is that because of this relation, the limit of epsilon going to 0 is actually equivalent to taking lambda to infinity. And so this can be done by considering an infinitesimally thin shell around this point, and then stacking them up until it covers the entire configuration space. So what we do now is that we first consider just one thin shell and see what happens to the fluctuation around such a saddle point. So here, what happened is that if we consider some thin shell bounded by the two shell here, defined by these two equations, we have that the fluctuation will be restricted by this equation. And so what we did next is we consider I represent the fluctuation delta x by c times n mu, and n mu is just a unit vector for the direction of the fluctuation, and c is some coefficient. So if we look at the change of the action delta s around this point, which is governed by the Hessian, and if we look at the large boost region along this curve, very far away, we find that the delta S here behaves like this. And in order for this to contribute to the Poisson function, we have to require that this is order 1. So now what we can do is that we have to set C coefficient here to be exponentially small, suppressed by at large boost here. So this means that the fluctuation whose magnitude is governed by this C is infinitely suppressed at large boost. So this is why we have that the quantum fluctuations are suppressed. and we get the
Sorry,
classification.
is it the first definition of sigma?
So sigma is a Lorentz boost parameter.
Oh, okay.
Yeah, sorry. Great, thank you. So now what we do is that we have to somehow tame the Lorentz symmetry. And what we propose here is that in order to properly account for the quantum fluctuation, we have to gauge fix the Lorentz symmetry. And what we do, well, Jun Nishimura has already introduced us to that. So I'll go here. So there is a suitable choice of gauge fixing it by minimize the x0 square. And this is, we can show that this is equivalent to imposing this kind of equation. And so by using the Faddeev-Popov procedure, introducing the determinant here and the delta function, so we arrive at the gauge fixed model. Yeah, and what we can do, a simple calculation is that we can consider the case of gamma into infinity. And in this way, this integral, we have that we can reduce this integral into this one. And so we can do the perturbative calculation. Yeah, and then what we found is we recover the quantum fluctuation, which we don't have before. Great. So now the lessons that we learned, just to summarize things up, is that the Poisson function diverges around the classical solution, which is associated with infinitely many number of equivalent configurations. So effectively, it's like those solutions that are associated with flat directions. And this is because of the non-compactness of Lorentz symmetry. And another point is that the Lorentz invariant observable will classicalize around such solution, and this is because of the artifacts of the Lorentz breaking time. Okay. So there's a question. Oh, great. Okay. So now we go back to the IKKT model. The result and the discussion beyond this point is actually will be appearing in the upcoming paper, hopefully this year. Right. So there are what we first do is that we consider d-dimensional bosonic model at n equal 2. Yeah. So what we found is that we have different classical solutions at positive gamma. So we have trivial solution, we have Pauli solution, and squash Pauli solution. This one, yeah, has already been introduced before. So the trivial solution is the one preserving all the symmetry. So Pauli solution breaks the Lorentz symmetry into this kind of diagonal subgroup, and the squash Pauli also break into a smaller one. And we call these two the non-trivial solutions. While on the other hand, the negative gamma, we only have trivial solutions. So we'll focus on all the solutions that appear here. Right. So now I will introduce you to something that we have already seen before in the formulation in the toy model, where we introduced the variable k. So what happened here will be quite similar to that. So first, as I emphasized before, that what you can do normally is we can do the perturbative expansion in 1 over gamma square around the classical solution. But in order to do some non-perturbative calculation, we will introduce some kind of Hubbard-Stratonovich transformation. And this kind of formulation is actually similar to what appeared in this paper as well, but there they consider the Euclidean bosonic model without the match term. So here for bosonic model, the number of D is just one parameter. There's no restriction. So what you can do is similar to what we have done before. Here I will consider only when in the case of epsilon going to 0 first for simplicity. And what we do is that we introduce an auxiliary variable like a Hubbard-Stratonovich transformation. And then we integrate out the original variable A, and we end up with this kind of action, originally in terms of h. And what we do is we do some rescaling of the variable and also the match parameter gamma in this way into h tilde and gamma tilde. And also, yeah, so so here is also transformed to this one, K2. So and in the end, you end up with this kind of function. And the effective action is given by here. Here I simplify a lot of expressions, so don't worry about that. And then what we have from the rescaling is that we have the factor of D here. And this is a good thing because then we can do some 1/d expansion at large D. And this will be an expansion that gives you some result that is non-perturbative in the last parameter. So this function is dominated at the large D by the solution of this saddle point equation, which is given by this one.
Question.
Yes.
Is it that K or log that K?
Oh yeah, log, yes. Okay, yeah, sorry, here too, yes. Right. So now let's consider some simpler model first before we get into the Lorentzian one. Let's consider just it's not a Euclidean, it just has a Euclidean metric, but we still have the factor of I here by doing this kind of quick rotation. So using the same technique that I have introduced earlier in the last slide, we will end up with this kind of effective action. And what we can do is that let's consider just a simple case of the saddle. Consider these answers. What we found is that the saddle point equation reduced to this kind of simple equation, just quadratic. And what we have is that at the negative gamma tilde, we can show that we only have one saddle, while for the positive gamma tilde, we have two saddles. And the reason why this is only the one without B plus here in the negative gamma tilde is because it's irrelevant in the same sense of the Pico-Lefschetz theory. This is a very simple flow equation, flow diagram that I can show about the being relevance or irrelevance. If we consider the case of epsilon going to 0, this is the kind of saddle point equation that we have. So clearly there is some singularity. So I should start with this one. So we have two saddles, right, in general, negative gamma and positive gamma. But we also have the singularity at the gamma tilde over 2. But so this is just like a sign for the fact that without epsilon, you cannot define a model in a well-defined way. So what we do is we, of course, introduce the convergence factor, and now the singularity is shifted downward, and this is the equation that we have before. Now what we can do is that we can look at how all these points along the real line flow in the holomorphic gradient flow. And what we found is what we find is that there will be a flow going to this saddle point B plus, and also a flow going to V minus saddle point. Sorry, I used a bit confusing notation here, but yeah. But this is what will happen in the case of gamma tilde, positive gamma tilde. But in the case of negative gamma tilde, as I have mentioned earlier, you will find that there will be no flow going to this kind of saddle, but only this one. Great. So now let's go back to the Lorentzian model. This is a kind of this is the Lorentzian model that we're considering. Now we introduced the epsilon in a different way, just because of the Lorentz symmetry. And we follow the same formulation of effective theory and large D scaling. So we end up with this kind of effective action. And so at large D, this Python function will be dominated by the solution to this saddle point equation. And we can solve for all the saddle points, and this is thanks to a paper by Jens that's kind of inspired us to be able to solve all of them. Yeah. So this is a list of saddles that we have. We have 5 of them. 3 of them is SO3 invariant. As you can see, it's proportional to the identity matrix. And the other two are Lorentz, well, SO3 breaking saddle, just it's not equal to this. So essentially, this kind of saddle, this is similar to what we have before in the SOD symmetric model, but we also have the new kind of saddle, and I'll explain how this saddle came up from the flow equation, flow diagram. The SO3 breaking saddle also has a similar form. This term is proportional to the identity matrix, but we also have some traceless diagonal term here as well. Right, and what I'll show is that these two saddles are not relevant from the Piccolo-Lipschitz theory. And what we can do to show that is to look at the flow diagrams again. That's what we have done in the SOD symmetric model. There we found that with the singularity, you have a flow that goes into both saddles at positive gamma tilde. But now in the Lorentzian model, you have different sign of epsilon. So obviously, there's two singularities now instead of one. Well, two kind, not just two, but yeah. So essentially, it's because this singularity is split into two, and what you found is that there'll be a flow between here that flow into one more saddle, which that's why we call it new, because it came up as a new one from the SOD symmetric model. And what we can show is that because there is a flow from the real line pointing exactly into this new saddle, that there is no flow from the real line to this B plus saddle anymore.
So when epsilon goes to zero, what happens to that singularity?
Yeah, it just come back to get just come back to this point on the real line. Yeah. Yes. Yeah, and so this means that this B plus, which is originally a relevant one, in the Lorentzian model it becomes irrelevant. But the V minus is still the relevant one. So we can in principle do the same for the case where we don't assume this kind of answers, but it's a bit more complicated, and we didn't focus too much on that. But we assume that it will be kind of the same procedure, that there'll be out of the two saddle that appear here, there'll be one that is irrelevant. So here we now end up with this the list of relevant saddle. We have 3 of them, and what we can compute is this kind of quantity, trace of edge, and here we only compute using the saddle point contribution. So you just take a trace with this kind of factor of here, and what you get is 0, 3, gamma over 8, and gamma for these 3 saddles. So now this is nice that they're all different, because the trace of edge can be compared to this kind of quantity in the IKKT, the original Lorentzian model. Yeah, and this quantity can be computed in the classical contribution. Just substitute the classical solution in, and what you get is that this saddle has the same gives the same quantity as the trivial saddle. So, and this is the same for the other. So the Pauli solution gives the same quantity, same value as this one, the new saddle, and the squash Pauli also gives the same value as this one. So by just comparing the leading order of the saddle point contribution, we can construct the correspondence between the saddle point in the large DIAS theory with the classical solution. So now, this is very powerful, because as I emphasized, that this saddle, the contribution, the calculation in these kind of saddle gives you the non-predictive results in mass terms. So, and this correspondence means that you can equate that to what you will found if you compute the same quantity non-predictably around the classical solution. Right. Okay. Just a little more detail. So you can also kind of see the correspondence by using the symmetry. apart from the trivial one, you can see that the Pauli equation is respecting the SO3 symmetry. And because the H and the A are related to each other by this kind of relation, where here we sum the Lorentz indices. So what this means is that this part of the symmetry, which come from the Lorentz symmetry, will be kind of hidden in the effective theory. So therefore, in the SO3 symmetry here kind of correspond to what we have in this kind of saddle, which is also SO3 invariant. Also the same for squash Pauli, which is respecting the SO2 symmetry. And this part is hidden, so it corresponds to this this kind of solution as well, which is also SO2 symmetry. Great. So now let's see the kind of similar situation that appears. So we have discussion about the artifacts of the Lorentz breaking cutoff. Okay. Yes, I have 15 minutes. Okay. Great. So right. So we have non-trivial solutions, and they break the Lorentz symmetry. So obviously we will have the flat version. And now what the lesson that we have learned from the toy model is that the existence of the non-compact flat direction imply the divergent Poisson function. And this is actually true. We have done the explicit calculation using the large D saddle. So this is the result that is non-perturbative in 1 over gamma squared. What we found is that for the trivial solution, this is finite because it doesn't break the Lorentz symmetry. So we don't have the infinitely many equivalent saddle along the flat direction because we don't have the flat directions. So this is perfectly fine. In the Pauli solution, we have that it's diverging like this, and also squash Pauli diverging in a different, well, the rate of divergence is different between these two solutions. And I just want to mention that this 3D over 2 and D come from the saddle point contribution, and this -6 and -3 comes from the fluctuation contribution. Yes.
What's the meaning that they don't diverge for specific values of D?
Oh,
does that mean anything?
I don't think there is a physical interpretation for that. It's just something that appears because D it's just another parameter in this theory. Yeah. Yeah, but that's an interesting point because we will from this divergence, because there is some point that kind of going to 0, and also there are some point that they're exactly the same. And because we consider the limit of f1 going to 0, we can consider we are allowed to consider just this divergent term without the other finite free factor that might appear in the exact calculation. Oh, yeah. So what we found is that if we equate this exponent, there'll be some critical dimension of d equals 6, where there is a transition between the Pauli solution that dominates the larger dimension and the squash Pauli solution that dominates the smaller dimension. And this is limited at d equals 3 because because squash Pauli has 2 non-zero component, while Pauli has 3 non-zero components. So smaller than 3, you only have squash Pauli anyway. Yeah. So what we do is that to confirm this kind of divergence, what we do is we try to confirm that there is actually a transition at d equals 3. And while we do that numerically, yes.
At d equals 3, is there any cancellation with the divergence?
Sorry?
At d equals 3, is there any cancellation?
Cancellation?
For the leading divergence, so they both diverge the same, right?
What do you mean by that? It's not diverging at the same way. This one is finite.
At the transition, sorry, at the transition.
At the transition. What?
So at the transition, both diverge at the same rate.
Yes.
So is there any cancellation between them? Maybe there's.
Well, in order to do that, you kind of have to consider another, the prefactor that are in front of these.
Right.
While we can do that, we're not particularly interested in that at the moment. So we kind of ignore it. I mean, at the epsilon going to 0 is well, okay.
Well, to
Yeah,
ensure
but
the
we-
divergence is that you need to guarantee it doesn't cancel, right? Because there could be accidental.
Okay, if you want to say that, then we can say that it's something around 6, if that's okay.
Right.
Yeah. Right. Okay. Yeah, but let me just say that I'm sorry. The finite terms are not really. Okay, let me just skip here. Yeah. So there is a prediction at there's this prediction of the transition dimensional at the equal 6. So what we do is we do the numerical simulation to confirm that. And so here, what we look at is this kind of quantity, the moment of inertia. So this is the usual quantity that we use to determine the dimensionality of the spacetime. And what the criteria for that, if we look for the number of large eigenvalues, and this will correspond to the spacetime dimensionality. And a specific quantity that is related to the matrix T here is the A3 here, which appear in the characteristic polynomial when we try to solve for the eigenvalues. So basically, A3 is written in terms of, can be written in terms of the matrix T like this. So it is a holomorphic function of A. So that is why that is the main reason why we can use the Lefschetz thimble method to compute this quantity here. Yeah, but in terms of the eigenvalues, A3 can also be written like this. And the important property of this quantity is that for this Pauli solution, we see that there are 3 non-zero components of the Boston matrices. So it kind of represents the 3-dimensional space, which you can interpret that you should have 3 large eigenvalues of this matrix T. So the A3 is a symmetric product of the eigenvalues. So A3 should be non-zero for Pauli solution. However, in contrast for the Squash-Pauli solution, which represent kind of like a 2-dimensional space, so there should be 2 large eigenvalues. And this means that no matter how you sum this one, there will always be 0 in one of them. So A3 will be 0 for Squash-Pauli. So this is clearly saying that you can use A3 as a kind of order parameter to see the transition. And we have done exactly that. It's very small, the number, but we can see the clear difference here. So for example, at d equals 4, the extrapolation to epsilon going to 0 is actually pointing towards 0 exactly. While if you do the simulation for d equals 5, 6, and 7, it kind of goes to some positive number, non-zero. So, and this clearly shows that there is a transition from squash Pauli to Pauli between d equals 4 and 5. Yeah, and the discrepancy can come from the finite epsilon effect that the fact that we cannot do the simulation at a smaller epsilon. Right.
Can you explain a little the symbols in the plot? So what is triangle and square?
The square is the simulation at d equals 10. No, the square is, yeah.
I see. So the upper one is squeeze.
Yeah, they're corresponding to different dimension. Yeah. Right. Right. So now there is another thing. We have kind of confirmed the transition or the power of divergence.
The
Sorry.
equal 5 is not clear where it's going, or
Equal 5 here, right?
because the transition is supposed to happen at equal 6.
Yes. So that's exactly what we meant here. So Yes, so we think that if we can do the simulation at a smaller epsilon, so yeah, the d equal 5 will go down here, and only d equals, I'm not sure about d equals 6.
6 is fine.
Yeah, I don't know, but clearly d equals 7 should be something logical. Yeah. Thank you. So now we have already talked about the divergence of the Gaussian function. That's one aspect of the Lorentzian model. Now from the toy model, we have another one, which is the classification. And we see exactly that in simulation as well. But I'll start from the prediction of how because it's a bit non-trivial looking at the toy model. So now this is the same picture that we used when we discussed the toy model. So we consider some cut-off surface exactly at the boosted saddle point along the flat directions. So, and then we looked at the fluctuation around this saddle point, and which is restricted by the cut-off constraint represented by this spherical curve by this constraint equation, similar to the one we have in the toy model. And what we do is that we looked at the change of the action in the same way that we did in the toy model, but here, so the change of the action is governed by the eigenvalues of the Hessian. So what we do is that we looked at these eigenvalues and see the behavior of them. For example, for Pauli solution, we found that there are 4 divergent eigenvalues and only 2 finite eigenvalues of the Hessian, and the rest are zeros. So this means that if we look at the ratio between the number of finite eigenvalues with respect to D, you'll see that there will be, well, these kind of finite quantum fluctuation will be suppressed at large D because of this factor, while the divergence is still going to remain there. So yeah.
Why doesn't 4 plus 2 doesn't add up?
The rest are zeros. Yes. Yeah. So now the divergence eigenvalues, you can relate this to the case where you have in the toy model that you have the divergence change of the action. But remember that we still have this coefficient C that we can set it to be infinitely suppressed or exponential of the boost parameter. So in that sense, this divergent eigenvalue represents the quantum fluctuation that are suppressed. So this means that at large D, we don't have any contribution from the fluctuation at all, and so there is a classicalization at large D. In contrast, for the Squash-Pauli solution, we have the same number of divergent eigenvalues, but we also have, well, the number of finite eigenvalues is proportional to D. So this means that with the same criteria of seeing whether there is any finite quantum fluctuation or not, we can see that only at D equals 3 that there is no finite eigenvalue, there is no finite quantum fluctuation at all. So this means that there is a classicalization up here at D equals 3, and not for D higher than that. So what we came up with is that this is a prediction. So if you look at the limit of epsilon going to 0 of this kind of quantity, we'll find the prediction is that for Pauli solution at large D, this should be the value that we get from the numerical simulation, and this is the value that we should get as well for the Squash-Pauli at D equals 3. And there should be some quantum fluctuation that appear if you consider, for example, D equals 4. Yeah, but we will not show here for the sake of time, but I can show you if you're interested. So numerical confirmation for this classification. So we consider Pauli solution at gamma tilde equal 2, and the classical prediction or the saddle point prediction is 3 gamma tilde over 8, which is 0.75. So what we do is that we do the simulation at d equal 10, 15, 20, and 30, and we do the extrapolation at large d at different epsilon. And what we found is that there is a nice linear conversion to 0.75, which is exactly the prediction that we have. And this is consistent to the prediction that at large d it should classicalize. Now, for the spot values, we consider gamma to gamma. Sorry. This is linear. Yes. Okay. So for spot value, we do the simulation at gamma equal 1.5, and the classical prediction is gamma over 2, which is again 0.75. And we found that if we look at the real part of the quantity that we are interested in at d equal 3, there is a nice convergence to 0.75 as well. And you'll see something different if you look at d equal 4. There'll be some deviation from this value. Very nice. We have a confirmation of what we have in the prediction. Totally. So now, in order to be able to recover the quantum fluctuation properly, because the cutoff is kind of like an artifact that cannot be removed even if you take the epsilon to 0. So what we do is we, again, like the toy model, we gauge fix the Lorentz symmetry by imposing this kind of equation, which is equivalent to minimizing trace A0 square. Yeah, and so, yeah, since the Lorentz symmetry also exists in the model with the fermions, even though we didn't do the simulation with fermions, we propose that we should, even with the model with the fermion, we should have imposed this kind of gauge fixing condition with the Faddeev-Popov determinant as well. And there is some kind of simulation evidence that appear in this paper, and also appear in Konstantinos talk before. And yeah, of course, with this extra term, the classical solution will be modified. This is discussed in this paper, and the numerical simulation has also been done using Lefschetz thimble and also the complex Langevin simulation. So to summarize, okay, sorry, just a couple minutes. So the functions around the classical solution that has the non-compact flat direction diverges because of the non-compactness of Lorentz symmetry. There is an artifact from the cutoff which remains after, even though we remove the cutoff by setting epsilon to 0. And this is appear as the classicalization. And so we propose that we need to gauge fix the Lorentz symmetry in order to properly take into account the quantum fluctuation. And the important thing is that, because the only thing that we have is that we have Lorentz symmetry and we have the cutoff. So this result extends to any system with the non-compact symmetry group. Yeah, where you have the saddles with the non-compact flat direction. So you have to maybe do this similar thing by gauge fixing the symmetry. Yeah, but that's all. Thank you very much for listening.
All right. Thank you for the invitation. That's the alarm from my car.
Okay.
But luckily I made it. I didn't miss it. All right. Sorry about that. So yeah, thank you for the invitation. And so I'm very sorry I couldn't attend the early part of the conference, but I look forward to talking to most of you. My name is Alfredo Guevara. I am at IIS Princeton. Most of this work I did with the time I was at Harvard with some collaborators there. We started looking into what the symmetry algebras of certain theories that go by the name of celestial conformal field theories have. So the real reason I'm here is to learn about matrix models from all of you. And I figure if I'm gonna be here and I'm gonna steal all the information you guys have from IKKT and all that, I should give you something back, some part of this very humble knowledge. But what I want to do is try to sort of motivate you and try to connect some dots in that there's another perspective in which we can understand matrix theory. So there will be a matrix theory, hopefully derived by the end of this lecture. So let me just give a little reference in case you want to check or you fall asleep and then you're like, what is this guy talking about? Okay, maybe let's open this paper. This is a paper I wrote when I was a student, and it has to do with the extended symmetry. And then there was another follow-up with Andy Strominger, Monica Him, Monica Perry, and Armina Himwich. So this is going to be most of the story. So without further ado, let me just give you the picture that I have in mind for this talk. Let's say that there is, as you know, there is a UV complete theory of quantum gravity that lives in the higher dimensions. And if you believe in the 11 dimensions, then you would believe that that theory is described by something we call the M theory. M here is for matrix, and this theory lives is fully quantum, so it doesn't have any sort of ambiguity or divergence, and hopefully it's realized by one of these nice actions that we've been hearing about, like IKKT and BFSS and BMN, all the kinds of magic that we have nowadays. But we don't live in inherent dimensions, obviously. So the way that this theory influenced our world is through some four-dimensional, say, compactification, right? And in fact, that what we observe, what we measure at the experiments happen to be some four-dimensional version in the landscape of vacuum of this theory. And here from our experiments, which are usually done at large particle colliders and maybe telescopes and so on, we can have some formulation of this UV complete theory, which goes by the name of EFT. So that's effective field theory that lives in the infrared, in the scales that we can currently measure. And so we can sort of construct certain completion of gravity in the way that we call usually the bottom-up construction. Whereas if you start with a UV complete quantum gravity, you usually derive observable measurements by something we call the top-down approach. Okay, and this for the EFT, believe it or not, has many of the magical properties of the putative UV quantum gravity theory. In particular, it has the notion of extended symmetries that are sort of a completion of what we usually call the Lorentz group or the Poincare group or the IDS group and so on. So this theory already has more information than just a naive four-dimensional theory. Okay. Yes, please. Yeah.
What theory has this?
So I'm going to show that what the constraints that we get just from these four-dimensional EFT theories have or involve a notion of what the extended symmetries are, which essentially comes from the fact that we're looking at some infrared region or regime of certain description, and in the infrared point, usually we have a CFT, and there is an emergent symmetries, like conformal symmetries.
Okay, so there'll be some assumptions, but you'll explain there.
Yeah, I'll explain a little what the assumptions are. But let me just sort of hint what the symmetries are. So we have heard in this conference, we have heard words like fuzzy. We have some fuzzy quantum mechanical system, the fuzzy sphere or fuzzy torus. And this system is associated to certain symmetries, for instance, of an infrared fixed point, like the Landau levels of a mechanical quantum mechanical system, right? So these fuzzy spheres are usually what condensed matter people call Landau levels, which are CFT, sort of described by. Maybe less familiar, or maybe for this audience, super familiar, the notion of WN algebras, which are also some kind of symmetries that extend the usual Virasoro algebra of just normal bona fide CFT. And the other symmetries, well, I'll just call them dynamical because they apply only when you write down the equation of Monte. Okay, so these are sort of some words that we have learned, and one way in which this picture is completed, it's by, of course, some matrix model that has very nice properties, but there is also an intersection here with what I call celestial theory. But I will, in particular, to be very precise, I will refer to the celestial here for the purpose of this talk as something I and many people have studied, which is self-dual gravity. Okay. So now I have explained self-dual. So from the UV theory, if you believe in 11 dimensions supergravity, we have highly symmetric excitations, those are called VPS excitations. And the simplest way of defining what the self-dual is the 4D reduction of VPS states. Okay, so just to give you, this is what I would call self-dual. So one example, for instance, is D6. It's a D6 brain that's compactified. So this D6 is VPS in 10D supergravity, and we compactify it on certain Calabi-Yau. In the simplest case, is a torus, so 6-dimensional torus, so that the D6 essentially looks like a point. And in our 4-dimension observation, this D6 is just a defect that sort of wraps this torus in the higher dimensions, but all we see is a point particle from the perspective of the 4-dimensional tube. So if you were to sort of couple a field strength to this D6 system, you will see that this field strength happens to be what we call self-dual, which is the fact that the Koch dual of this field strength is equal to plus or minus I, depending on your conventions, itself. Okay, and this usually just means that the electric field sourced by this this brain, it's some kind of Karl-Ramon field in 10 dimensions, but in 4 dimensions you just see this electric field equal the magnetic field. Okay, so what does this mean? Essentially, it means that there is a cancellation because this state is highly symmetric, and so if we put 2 of these guys together, they won't interact, like they won't deform.
So these are these 2 forms or 3 forms?
Sorry, these ones are 2 forms. Yeah.
3 forms.
No, these are 2 forms.
2 forms, right?
It's not the Karl-Ramon field.
So that's fine. But then you have some kind of Lorentzian signature.
True.
Otherwise, you couldn't have an I there.
Yeah.
So the group has to be non-compact.
True. Yeah. Yeah. So in fact, many of these solutions, if you just think of them as Lorentzian, they will be complex because of the fact that there is an I. So in particular for self-gravity, the metric itself will be complex, which you may consider to be a problem. I mean, we know that in the Euclidean signature, this is fine, it's just an instanton. But whenever that becomes a problem, for reasons that are explained in these papers and in a follow-up, the sort of precise definition will be given in 2,2 signature, which is a signature that allows me to delete the I from this equation.
So you said there, I didn't catch the word supermodel.
No, 2,2 signature.
Okay.
Yeah, that will delete the I. And that makes the solution real. If you're writing down the metric, it would be a real metric. This also goes by the name of Kleinian spacetime as opposed to Minkowski spacetime, because Klein actually figured this out even before Minkowski, but that's a story for another day. So suppose you have two of these guys, you have two D6 brains. Because of the cancellation, they actually don't attract or repel each other. It's a BPS state. So to make it dynamical, to make some kind of dynamical symmetry, what we have to do is we have to add something that is not exactly BPS, but it's half BPS, as it could be a D0 brain, which is just essentially a point. And this point it's in this case interacting with the D6, and this is called the D6 D0 system. It's a half BPS state. That means there is some dynamical construction, and the sort of construction, if you look at the effective metric sourced by a stack of this D6 brains, suppose I have N6 of them, and suppose I have a stack of N0 D0 brains. In the case of N0 being sort of no part reacting on the D6 system, what I have from the 4-dimensional picture is something like called self-dual metric. Okay, and the precise word here is tau-nut. If you have heard about the tau-nut solution, that is what it is. Okay, so there's an effective metric that this guy observes, sourced by the D6. Okay, so that's just how I describe what a self-dual system is. It's a system that has a BPS state and a non-BPS state, and they interact. But from the 4-dimensional perspective, there's nothing like BPS. And in fact, this system doesn't really need supersymmetry. I mean, you're looking at this infrared description of the system. There's no supersymmetry. All there is a field strength that is self-dual. Okay. So in some of my talks, I call this like the bosonic version of supersymmetry, simply because you can describe it from the 4D world, and it doesn't have any construction. You don't really require to construct it from supergravity.
So in the number of D0 brains is small, so they're just in the probe approximation.
Yes, this is the probe. So this is
why
the
do you
metric.
need them at all then?
What?
Why do you need them? Because they're not disturbing the geometry.
They are not disturbing the geometry, but I want to evaluate the motion of this D0 in the background of.
So you are using them as probes.
Yeah, yeah. To compute the metric, I mean, you need to approximate something. No one knows what the exact metric is, although there are some ideas. But when this is a probe, then you can write down the metric explicitly, and it's this self-dual tau-nut. And this actually is a very exact solution. So it's exact. Sorry. It came a long time ago by approximating the motion of two dions, which are very, very far apart. Sometimes called Kaluza-Klein monopoles. So if you have one of these Kaluza-Klein monopoles that come from 5 dimensions, so on. In the 4-dimensional case, they move as if one were a geodesic in respect to the other background. So this is actually KK monopoles. It's just another name for this story. It's the relative motion. the relative motion of these monopoles. Okay. If the monopoles could come closer together, then you have something called the DIAS symmetry, which is not exact, it's some elliptic integral, and things become more intricate. But if they are far, then it's this, and it's an exact closed solution.
So there is an S1 hidden in here.
And S1?
Yes, the kilotic line.
Yeah.
So it's twisted. Okay.
Yeah. The S1 is related to the mass of the model. Okay, so any more questions? This is just a way of introducing what the self-dual universe is, but you know, there's a lot of mathematics that I'm also not describing. I could write the exact metric, but I'm not doing it. Okay, how do I continue? Do I continue here? Sure. Okay. So if you assume that there are many of these BPS states in 4 dimensions, it will look as something like this. So you have your, at first order, if you want, you have this Minkowski spacetime. There are these BPS states that are interacting. Some of them are coming from the asymptotic past. They go to asymptotic future, but they all source the field strengths that are self-dual. So I denote that by plus. And because there is no interaction, the scattering amplitude, which occurs when I source the BPS states, is 0. Okay, so that means they don't interact. So to make it interacting, I have to input some kind of probe, and if I were to write the field strength, it would have to have a minus component so that they interact. Okay, so now I'm sort of appealing the intuition that plus and minus are interacting, but plus and plus are not. Okay, so that's sort of helicity conservation here. It turns out that for some reason, that is not obvious, but it can be shown with supersymmetry. These amplitudes vanish, and they only become non-vanishing when I have 2 minus states. Okay, so this is usually, I mean, in the textbook calculation, this is called the supersymmetric Guevara identity. If you have supersymmetry, okay, which is that amplitude with 1 minus and all the other classes vanishes. Okay, I don't know if you can see. Okay, but the one that has 2 minuses is non-trivial, but you can see because it's the lowest level of complexity, it has to be very simple. And indeed, it is very simple. But to write it down in a simple form and not using Feynman diagrams that extend a long computation, I need to describe the kinematics. So how do we set up this problem with equations? Let me just say that what the word celestial means. So I'm gonna just briefly explain what the word celestial is. It just means that I will be describing these kinematics in this asymptotic non-infinity regions. Okay, so I will describe each of these particles by their position in the celestial sphere. So there is a S2 at non-infinity. Actually, more precisely, it's a CP1. It has an SL2C symmetry group, which is essentially the Lorentz group acting on non-infinity. And this non-infinity is parameterized in bonding gauge or whatever way you want to write it by a complex variable set. If you want, it's something like EI phi over 2 tan of theta half, where theta and phi are dangles on my sphere here, and an energy. That energy is omega, which is the energy of positive if it's an outgoing particle, or negative if it's incoming. Okay, so those are the 2 variables that are going to play in this game. So given these 2 variables, I can write down what the amplitude with two minuses is. Okay, so now I'm gonna click erase. Okay, so in the case of gauge theory, which is the simplest case, this is called the Park-Taylor formula. In the case of gravity, with coupling is called the Hodges formula. And I'm gonna describe the kinematics a bit more precisely. So I mentioned that the group is SL2C. So to transform momentum vector, which is the momentum of each of these particles, according to SL2C, we use the spinor variables. And these are called the spinor helicity variables. So I take my Pauli matrix with 4 dimensions. It has an SL2C spinor and conjugate index, and I hit it with my 4 moment. Okay, and that I call P alpha alpha dot. Okay, and if my particle is null, that means it's a graviton, right? So remember that gravitons always go to non-infinity, but if you have some massive particle, it will go to time like infinity. So in this case, I'm just going to consider gravitons. Can be plus or minus according to that picture. So these are states where there is no mass, and so if you pose this condition that p squared is 0, you find that the determinant of p alpha alpha dot is 0. And then that tells you that this is a singular matrix, and so it can be written as a direct product of 2 variables, which are lambda and lambda t. Okay, which are actually by the spinors, right? So each of the action of SL2C will act in a linear 1/2 way on lambda and lambda tilde, sorry. And that's essentially gonna be the Lorentz group. So so the SL2C acts in this way. At this point, I'm just setting my notation here. And it turns out that to connect to these variables that parameterize the celestial sphere, what I do is I sort of take out the scale of my lambda. So my lambda now, I parameterize it by 1. It's a projective frame, and the overall factor I just call omega. Actually, let me call this square root of omega, and let me parameterize square root of lambda tilde with the square root of omega 2. And you can check that if this momenta p mu is to be real, then Z and Z bar have to be conjugate, which means that what you have is a celestial, is a sphere. When Z and Z bar are conjugate, it's just a CP1. But moreover, it's a CP1 because it has a conformal transformation. So if you go, you are on a rocket ship, and then you go and change your frame, this sphere will rotate by this law, which becomes written in terms of Z coordinates if it becomes the usual conformal transformation. So that means that Z is a coordinate on CP1. And yeah, so I just described to you what this set is and what this omega is. Let me just see if I need to describe any other component. Okay.
Well, is your order identity is going to follow from these kinematic observations?
No. So the word identity is sorry, you're talking about this.
Yeah.
Okay, so this is supersymmetry. It's more.
Oh yeah, it's a supersymmetry.
Yeah, it's more general than this. This is Lorentz symmetry, right? But it's a 4D Lorentz symmetry. So you may mind that if this is a really higher dimensional system, like it came from a higher dimensional theory, there is something else that extends this Lorentz group to be the full SO10, for instance. And in fact, there isn't. So that's kind of the explanation for this extended. But I haven't really gotten there yet. What I will do now is well, I will do two things. So first, in order to describe the formula, the simplest way to diagonalize SL to C is by interpreting this amplitude as a correlation function that lives on the sphere. So it's a correlation function that lives instead of writing A as a function of the momenta, I'm going to write A as a function of the positions in the sphere. But you can check that if I just take the amplitude and write it in this form, it doesn't transform under SL2C because of the fact that this omega here. So you remember that this half weight half 1/2. So omega also has to transform in the following way. So it transforms as a density under SL2C. So essentially something like this. Sorry, there's a square root. Again, this both follow from this law. So this is the Lorentz group. But the fact that the amplitude depends on omega and Z immediately tells you that this cannot be as a normal correlation function we will write in a CFT. So for that to be fixed, the main actor in the story is going to be what mathematicians have played with for centuries called the Mellin transform. Okay, so you take the energy of each of these particles, you integrate it depending whether they are outgoing or incoming. So it can be plus or minus infinity. And essentially you add a weight that represents the conformal weight of the particle at position Z1 to Zn. Okay, so here I take omega 1, and then I declare that the particle inserted at Z1 is going to have weight delta 1. And I do that. I'm sorry if you cannot see, but it's the same for all the energies. And I do that to my amplitude.
It is visible on this.
Oh, it's visible on this? Okay. How about here? Okay. And my amplitude is written
towards the edge of this.
Okay. Okay. My amplitude is written in terms of omega and Z. Omega 1, Z1, up to Z. So if I do that, then this becomes a correlation function where particles are inserted at Z1 to Zn, but have weights delta 1 to delta n. Okay, and that this is just a kinematic trick. I haven't touched the theory. I can do this actually for any state, doesn't need to be self-dual or BPS. In fact, this is a particular case, but as long as I apply this rule, the Lorentz group, just the kinematical part, will be seen as conformal symmetries. Yeah.
These integrals are not convergent.
Good.
So you're kind of doing something that under certain distribution senses overlap. So
good. So well, that is a statement that depends on the integral, right? So it's a statement of the integral. So I haven't told you what the integral is. In general, you're completely right. There is no convergence. You may worry about two things: 0 at infinity. I'm not going to explain each of them, but I'm just going to say these are what in physics we call infrared and UV regimes, where the energies are either small or large. Both of them have a physical interpretation. So in the UV, we believe there will be a theory that has asymptotic softness, so it will behave just like a string theory. We will be damped by some radial trajectory. And in the infrared, actually, this is more important for us because we're looking at the infrared. There will be a divergence which is under control. So we can use the theory of analytic continuation to define this integral in a complex strip in the complex delta plane. So the bands of the strip will be related to the degree of divergence of my amplitude in the infrared, essentially. Okay, so that's one thing. So actually, that's essentially what the first paper, this paper, is about. So this paper is called soft. I don't remember. It's something that has soft theorems in the title, and that tells you what happens as you go to omega goes to 0. So for instance, here I'll have to explain something. Am I going too fast or too slow, or is just okay? Perfect. Okay. So, how much time do I have?
20 minutes.
20 minutes. Okay. So let's just review a little bit of that. So I'm going to be a little schematic here. The formulas are in the paper, but roughly speaking, there is something that in physics we refer to soft terms, and it's derived by Weinberg originally, but then it was extended to many contexts, and by now we understand it more or less in full generality. And there's a statement that if I take a function of the kinematics, so remember this depends on omega and z, right? Omega 1, z1, and so on. And I take one of the particles to be very soft, so omega 1 goes to 0. The statement is that there will always be, in any theory that has constraints of causality and unitarity and all of those, there will be 1 over omega 4. Okay, and this will be the leading order. And the factor of this, so the residue at omega goes to 0, is going to be the amplitude schematically without the particle 1. So it's going to be some amplitude that depends on the hard date. Okay, this is universal. Okay. However, I was mentioning soft-dual theories and how magical they are because we have many symmetries. In the case of self-dual gravity, and this is where I come back to this amplitude that has two states of minus helicity. So let me call those states plus. I have n minus 2 classes, and I have two minuses. So if the notation is not clear, I assume that there are n minus 2 classes. And it so happens that even if I don't take the limit, well, obviously there's still 1 over omega pole, which is universal. But there are corrections. So here you can come up with corrections that look like powers of omega. But in fact, you can also compute, if you go to one loop, beta function, there will be a log of omega correction. So there will be all kinds of weird things. But here, in this amplitude, actually, the corrections are all resummed into an exponential, okay? And the exponential happens to act, again, the same thing. The amplitude starts with 2. And each of these particles has an angular momentum operator. And it's essentially that. So I just sum over particle 2 to n. And I act in each of these particles, I act with the angular momentum operator, which is, as I just described, is an SL2C operator, right? So it's an SL2C. So this is kind of an SL2C transformation because it's generated by the angular momentum with some. So this only happens in this case. And it's sort of magic that we attribute to the self-dwell point. If you want references, well, okay, I derived that in that paper, but essentially it goes back to some magical formula derived a long time ago by Andrew Hodges, who was Roger Penrose's student, and then went on to write the biography of, if you have seen the Enigma Code, that was written by him, the novel of Alan, the biography of Alan Turing. So he has done all kinds of amazing things. In my personal opinion, highly biased, this is the most amazing thing he has done. But the movie was really good. So okay, so we have this formula. And now we can come back to the previous question. So imagine you're given this expression. Let's forget for a moment that this Ji is an operator, okay? It's matrix value, SL2C generator, differential operator, whatever you want. But just suppose that it's a number that's negative, okay? Yeah, so we get some intuition. So if you were to plug this into that, and you were to execute the integral over omega 1, you will find that the integral looks like this, times 1 over omega, that's always there, times an exponential of omega times a number that I refer as a negative number. Or if you want the eigenvalues of negative. Okay, so if I do this integral, and if I remember correctly, this gives me some power of gamma, sorry, of J, times the gamma function in delta. Okay. So this perfectly. This one, yeah. Yeah, it's sorry, you mean minus delta or?
No, delta minus 1. Because that's
Oh yeah, sorry.
Delta minus 1.
Oh yeah, sorry. Yeah, you guys are keeping close eyes on my formulas. Great. So yeah, obviously this formula is not true because J is an operator. But there are two things that are important here. First, it's perfectly defined analytically. So we know that the gamma function is convergent on a strip. The strip is starting from the zero of this thing, which is delta equals 1, all the way to the right. There is no poles, it's analytic. If you go one integer past the pole, so to say, you need to do an analytic continuation. So just to remind everyone, I mean, maybe just to remind myself, there is a delta equals 1 pole, and then there is a delta equals 0 pole, and so on. And in each of these strips, the function is convergent, the integral is convergent, it's defined by analytic continuation, and so is in the strip that goes all the way to infinity. Okay, so this is in the delta. Of course, that's not true because this is an operator, it's not a number. So what do we do going back to this formula? So what we do is even if this is not true, the formula that you get when you evaluate this as a residue at a pole in delta gives you a residue, which is a power of j, which is true as an operator equation. So let me just write that down. So these are going to be these extended symmetries that I was mentioning. Okay. Okay. I don't want to break this. Okay. So. Okay, so the statement is that the residue of the amplitude, just as a function of Z1, delta 1, as delta 1 goes to a negative integer plus 1, is controlled by a sum. So now you take the residue of delta equals 1 minus n here. And then you should see that you get a power of j, which please don't correct me because I'm probably gonna not get it right, but it's something that is order n, acting on the particle, on the amplitude without the particle too. Delta n. So I have effectively removed particle 1 by taking a residue in this function, and I remind you this function is a 2D. It behaves as a 2D correlation function. It doesn't mean it's exactly constructed by the axioms of CFT, which is a bit delicate. But if you believe it transforms a conformal correlation function, then this is just a statement about the spectrum of this conformal correlation function, which has some resonance at particular points. Okay, so I've been a bit sloppy in defining the correlation function. We have axioms in CFT. Some of them are not true here. Particularly the central charge, if you were to compute it, would be negative. And there are other things that require more care. But the overall upshot of this story is that we have a statement that looks like this for any n. Okay, for any n that's a positive number, and so we call this, and we have very important reasons to believe that it is an infinite tower of Ward identities. And in fact, later we realized that that infinite tower just goes by the name of W 1 plus infinity algebra. Okay. So this is where the story becomes interesting. But how much time do we actually have? 8 minutes. Okay. Let me just leave that for another day. Is there any question about this so far?
if you choose the kernel in a nice way, can you actually explicitly evaluate these integrals? I mean, there's some nice formula for them.
Good. Yes.
Satisfy any nice differential
Yes.
equation.
Yes. Absolutely. Yes. Good. Yeah. So maybe I'll spend the last 8 minutes explaining why these integrals are well defined. Okay. So the first example that we can compute is a string theory. So we can compute an amplitude coming from some string compactification in 4 dimensions. And in that case, the behavior as omega goes to infinity is exponentially soft, because that's just the softness of the Veneziano amplitude or Virasoro-Shapiro amplitude. But what's more interesting, so we can compute that at 4 points. So if you have only, say, 2 minuses and 2 pluses, okay? So that one is the Virasoro-Shapiro amplitude. If you look at the large omega, how it behaves at large energies, at least at weak coupling, okay? Then it literally has complete control over the UV. The IR is exactly the same story as here, and more generically, the statement is that you need to sort of organize your energies into what's called the EFT expansion. So the law of EFT is that you will see some effective theory at the infrared, and as soon as you start increasing the energies, there will be new operators that pop up at each of the resonances that you are probing. So if you are doing the experiment and you throw some highly energetic particles in here, there will be an effective energy, which is the mass of the intermediate state, where there will be a correction by a new operator. So that's sort of the EFT in a nutshell. And what that means is that I can write down my amplitude. So this amplitude in an expansion, which is a sort of Taylor series expansion as omega goes to 0. And the power of that expansion is essentially going to determine where the poles are in delta. So so we can do the exercise of saying something that looks like this. Now I insert an EFT operator with some power, and this is only defined when I have a series. It is not defined for each power, but you can sort of convince yourself that this gives you a pole at the location alpha. Okay, yes, single term in the EFT expansion will give you a pole. If you have an infrared divergent thing that looks like log of omega, for instance, that will turn into a double pole. If you have many powers of log of omega, then this will just become higher order pole. Okay? Yeah, it's a system of the many transform, yes. But the interpretation is that the many transform amplitude, which is this correlation function, has resonances at the insertion of these operators that I start adding when I do my experiment. Right? So I draw certain operators as singularities. Yeah, I think that should be enough for today. But let me just give you a little preview of how these other things came up. Now, I mentioned there is an infinite tower of wire entities. And it turns out that if you consider so this tower of wire entities exists for any number of particles. So I can just keep adding insertions of these plus states. Once I add infinitely many of these states, what I make essentially is a coherent state, which is a background of self-dual gravitons. And that's what we call the BPS state. So the BPS state, the state I mentioned at the beginning, which is the self-dual tau naught, is just a coherent superposition of many of these particles. All of these are plus states. You probe this metric by a minus state, just how I mentioned it for the D0, probing the D6. So you probe this self-dual background with a minus insertion. And then this self-dual background, by transitivity, if you want, has an infinite tower of W symmetries for a negative helicity probe. So this is this is what leads to the dynamical symmetry for a probe. But I think I'm running short time to explain this. Probes. Okay, and there's another layer of the story which again is missing, but all of these theories admit a description in terms of twistor Lagrangians or twistor actions. And it's the twistor action that is built on this algebra, and it's a twistor space that is, in a sense, the fuzzy sphere. And I know I am very much overselling this because I can't explain not even what a twistor is. But this is the connection. Okay, there's a twistor. There's a twistor action description of these symmetries, and we can, in a very precise way, map this twistor action to a fuzzy sphere. But I'll just leave it. I just leave it there for today. So I'll stop there.
Thanks for the invitation, first of all, even though I'm not showing up in person. I want to present some results on the ground state of SU2 Young-Mills quantum mechanics. So in this talk, we will be seeing a few new results that haven't been published yet. The paper is still going through my publication approval internally at Google. So everything that we hand out has to go through a publication process. Overall, I'm doing this mostly in personal capacity, but for academic purposes, my correspondence address is via Google. So technically, I'm in terms of research affiliation an employee of Google here. So let's look at a problem in quantum mechanics, and then, well, we will be looking at the problem of finding the corresponding ground state. We will take a first peek at the ground state, and later I'll show how to do the calculation, and then we perhaps will have a bit of Q&A. Can you see what I'm presenting?
Yes.
Oh, okay, everything good. So what is the problem and why is this tricky? So the task is as follows. We want to find the ground state of a nominally very simple two-particle quantum mechanics problem. So space is three-dimensional, and nominally we are looking at motion of two particles in joint potential. So our position coordinates are in total 6. So we are in 6-dimensional space, but we can rearrange these in terms of the position coordinates of the first and the second particle. I'm calling these x0 and x1. I'm always starting index counting at 0. And my Hamiltonian is just the kinetic energy, so p squared over 2m, that becomes the Laplacian on the quantum state. So Laplacian with respect to the coordinates of particle 0 plus Laplacian with respect to coordinates of particle 1. Well, minus from partial integration. And then I have this potential term, which is the square of the magnitude of the cross product of the two particle positions. And in this system arises when we do toroidal compactification of Young-Mills theory and take a particular limit. So it's basically the first interesting Hamiltonian that we get in a series expansion. And this is nicely explained in a 1983 paper by Martin Lüscher, where he shows how to obtain this from Young-Mills theory. But surprisingly, there's not that much apparently that has been known so far about the ground state. And I came to this problem when I met Jens Hoppe at the IAGS. I was visiting Thibault d'Amour in 2023, and he showed me this, that he was working on a paper on this problem, which meanwhile has been published. And by basically taking his ideas a step further, I could find, I would say, a convincing proposal for the ground state. And here in this talk, I want to convince you that for this particular Hamiltonian, there's compelling reason to think that the ground state has energy approximately this value E star I keep referring to of 2.1107035522948805. And it should be good to as many digits as I'm showing here. And of course, if we wanted to have a higher accuracy, then we could just invest a bit more compute and get better results. So in what follows, I will be talking about relative and in particular absolute tolerances. And that raises the question how I'm normalizing my ground state. And I want to normalize it such that the largest amplitude, so I will use an all real ground state naturally. And the largest amplitude will be at the origin, all 6 coordinates 0. And I want to normalize it to 1 there. But square integrability is nevertheless given because I'm basically getting this as a convergent series in square integrable functions where I expand my Hilbert space from step to step. And it's very plausible that actually I have a solution there and that it is square integrable. So if I'm looking at the deviation between h psi star, where psi star is this numerically obtained ground state, which I then actually turn into a proper function of 6 coordinates. And if I apply the proper, as well as I can do it numerically, so not on the constrained Hilbert space on which I did the calculation, if I apply the Hamilton operator to this and then see how far off my E star psi star is, just scaling psi star by this E star value which you see above, then what you find is that you can express the deviation in such a way that you have a certain relative tolerance that's just proportional to E star psi star, and then an absolute tolerance. And we can get it such that for the average length of the vector x0 and x1 being at most 4, we are good to an absolute tolerance of 10 to the minus 9 plus a relative tolerance of 5 times 10 to the minus 7. So this looks quite reasonable, and if one keeps increasing the size of the Hilbert space, it indicates that we are converging to that value, but of course this is not a stringent mathematical proof. So what we see if we look at this Hamiltonian is that there's an obvious O3 rotation symmetry. So not just SO3, 3-dimensional rotations of all spatial coordinates, but also mirroring will be a symmetry due to the square in the cross product. But actually, if we look a bit closer, we find that there is even more than that. And this is something that, for example, Jens looked at in detail in his 2023 paper. So there actually is an O3 cross O2 symmetry. And for example, this shows pretty much straight away if we just rewrite the potential term here. Here I wrote it with all the indices. And we have 2 types of indices. We have a spatial index I. In my case, this goes 0, 1, 2. And n then is the particle number index. This is just 0 or 1. What we now can do is that we can use this SO2 invariance that kind of mixes the 2 position vectors x0 and x1. And well, I mean, this is just a rotation between these 2 position vectors. And if we want to work it out explicitly, then for the angle phi, rotation angle phi, which I'm giving below 1/2 arctan, the difference in the length squares of the vectors divided by twice the scalar product. With that particular rotation angle, we will make the length of these 2 vectors the same. And what we then can do, so far we've only used the SO2 from the O2 part. We can then use a special SO3 rotation to make the X naught prime, the length aligned X naught point in the X direction. So make this a multiple of 1, 0, 0. And then we still have a SO2 rotational freedom, which we can use to set the Z coordinate of X1 prime to 0. So then we have X1 prime in the form XY0, and X naught is given by square root of X squared plus Y squared 0, 0, clearly. So this means that if psi naught is our ground state, then we can introduce two auxiliary functions of two parameters, and I'm calling these psi naught tilde, R alpha and XY. So the one is expressing things in terms of R and alpha coordinates. R is the length of the X naught, respectively X1 vector, after I made them equal length with this SO2 rotation. And alpha is then the angle between these vectors, respectively. I can also implement this in terms of the XY coordinates of my X1 vector. And when I'm showing plots, I will be referring to this psi tilde of R alpha, psi tilde of XY. They contain the same information as the full 6-dimensional ground state function, clearly. So we should be good here. Now, what's the problem here? Why is this tricky? And if one thinks about the structure of the potential, then one finds that this has flat valleys, where the two position vectors x naught and x1 are approximately parallel, right? And what I'm showing here is not just the three-dimensional surface plot of the potential, but also at the bottom I have a contour plot of the level surfaces. And this clearly shows that while this valley here always goes down to 0, that the valley that we get when x naught and xy are parallel, the longer these vectors get, the narrower the potential will become. And however, in principle, we could imagine that then the ground state for this quantum mechanics might actually stretch out very far along these valleys. So this is something that, in principle, at first, we don't know to what extent this might be an issue. But, well, let's actually look at the numerical results and see what they suggest. So this concern that the ground state might be very stretched out turns out to be actually quite pessimistic. So before I show plots, I have to explain what they actually present. So we take this form of the ground state in terms of R and the angle between the vectors alpha. The potential is clearly symmetric under flipping the sign of x1. And this means that in our alpha language, we have this symmetry around angle pi half, angle 90 degrees between the two vectors. So also, when we think about it, angle 0 between the two vectors mean we are looking along one of these valleys where the potential is 0. As we then increase the angle between the vectors up to pi half, up to 90 degrees, along these rays, we are climbing onto an ever steeper hillside upward. So one would naturally expect that the ground state constrained on these lines would then correspondingly decay the faster, the larger we make this angle from 0 to 90 degrees. And this is indeed what happens. So that means that in a plot, I can just plot this psi naught of R alpha as a function of R for given alpha, where I'm taking, let's say, evenly spaced subdivision of the angle from 0 to 90 degrees. And here I'm going by 1/6 of a 90-degree angle, and that gives me 7 plots. And well, this will allow us to compactly show a lot of information. So basically, if I wanted to see how the amplitude looks like when I'm going along the valley, then this would be the topmost curve of these 7 curves. Then for 1/6 of 90 degrees, it would be the next one just below it, and so on. So we can one-to-one identify which curve corresponds to which direction in the potential here. And as we see here, the dependency of amplitude half-width, so 0.5 is here, on direction is actually really not large. If we talked about probability density 0.5, then it would be even less. But of course, what we see is that there's some noticeable dependency of the rate of fall off in direction. But if this really is the ground state, then the observation is that the potential actually manages remarkably well to keep the ground state confined, even along the direction of the valley. Okay, so let's actually look at the numerical quality of this claimed ground state here in this plot. Now we are switching to XY coordinates, and I'm showing H psi tilde, where H is the exact Hamiltonian implemented as a differential operator, but with finite differencing applied to the ground state, which I got on a constrained Hilbert space, on a finite dimensional Hilbert space, minus E star psi tilde, using the psi star, the E star from beforehand. And what we find is, so near the origin, the deviation between H minus E star applied to psi tilde is everywhere in absolute values smaller than 10 to the minus 11. So the contours that we see are the magnitude 10 to the minus 11 contours, the contours that we first hit when we go out from the origin. The dashed contours mean that the deviation is negative, and the solid contours mean that the deviation is positive. So the first one is 10 to the minus 11, and then every further contour doubles that value. So the next one would be 2 times 10 to the minus 11, 4 times 10 to the minus 11. And everything inside here out to a distance of r equals 4 is in the interval, so the deviation in absolute terms is definitely between minus 1.1 times 10 to the minus 9 on the negative side, and on the positive side 4.3 times 10 to the minus 10. And this is basically what you can get by well, tasking a single CPU on a machine with 64 gigabytes of RAM to do the calculation over the course of one day. So this is very doable. And if we really wanted to have things more accurate, we could just expand more compute, as I said. Okay, now going back to this plot, we might, of course, want to know how fast does this function fall off, depending on direction. And what I can do here is to just plot the logarithm as a function of r, again, log psi as a function of r. If we had Gaussian, then of course we would get a parabola, minus 1/2 x squared. So here visually it might be a bit difficult to see what the deviation from a parabola looks like. So let me do the following. I mean, whenever I'm in a situation where I'm expecting a power law, I can of course do a log-log plot, and then the power law behavior would show as a straight line. So I'm actually doing a log-log plot of log psi. And what I'm also doing is I'm subtracting the slope 2 that I would get for a Gaussian. And this then looks as follows. So out to something, and this is the natural logarithm, so e to the power minus 2 or so, there's barely any deviation from a Gaussian. But here I'm going, I would say the numbers are reliable to even beyond log r equals 1, so r beyond 2.7 or so. And here we see that we do get positive and negative deviations from the power law of a Gaussian. Now, this is what the numerics tells us. So a few words on how to actually do this calculation. And ultimately, we need three ingredients. Basically, this is a problem in elementary quantum mechanics. So clearly, we need a bit of that. Then we will have to exploit the invariant theory of O3 cross O2. And then, as we will see, we need to have some way of doing high precision numerical matrix calculations. Here, I did it with the MP-Math package, basically due to some preference on my side for open source approaches, but Mathematica could do this as well, I would say. There is, however, some fine print. So when I try to take a head-on approach for this calculation, I couldn't do it straight away. And I actually first did a detour where I replaced R3 cross R3 with S3 cross S3, so that by making my space compact, I have square integrability enforced automatically. And then one has to be a little bit careful in terms of how one takes the limit. So one has to scale up the potential in order to constrain the ground state increasingly to increasingly small regions around the north pole of S3 cross S3, if you want so, while at the same time sending the cut-off maximal Fourier mode on S3 cross S3 to infinity, that we still get a reasonable limit. And the beauty of this is that the Laplace operator on S3 also being the group manifold SU2, is very easy to understand and is in direct one-to-one correspondence with the representation theory of SU2. So we are basically looking at the Fourier modes on S3, and these are the same as the Fourier modes on SU2, and these are the irreducible representations. So doing the calculation that way, one finds that E star is larger than about 2.09, a little bit larger, and basically having done that earlier calculation, I then saw what my problem was when I tried to wire up this more straightforward flat space calculation, and I could fix this, and this is how I actually got that result. But let's look at the streamlined calculation. So basically, you know how to wire it up, and you learned how to debug it. What does it look like in the end? So what we already know about this problem is that there's a single non-degenerate square integrable ground state. This has been found in the literature earlier. And what we also know is, well, looking at representation theory of this O3 cross O2 symmetry, all the invariants of O3 cross O2 that are polynomial in coordinates are finite linear combinations of u to the power a, v to the power b, and I'm putting a tilde on top of these quantities because they differ from what Jens has in his paper by rescaling, but morally they are u and v, where v is just the potential, or well, twice the potential. So this is quartic in coordinates, and u is the sum of the squares of all position coordinates. What we then also introduce, and this is the thing that makes everything square integrable in our basis functions that we will be looking at in a moment, we introduce this x minus u tilde half. So this decays exponentially and isotropically in 6 dimensions, just a 6-dimensional Gaussian. Now, we can define basis functions BAB, labeled, indexed by the exponents of a and b of u to the power a, v to the power b, and then exp minus this u tilde half, which is just this e tilde that I introduced here. Now, what one notices pretty much immediately is that with respect to the natural scalar products, so everything is real here, I don't have to complex conjugate, so just the product of some BAB with some other BCD over all 6 coordinates of my 6-dimensional space. So this is not an orthonormal basis, but that won't be a problem. Now, what do we need? We will need these integrals, BAB, BCD, integrated over 6-dimensional space. And we will also need BAB Laplace BCD for the kinetic energy term, also integrated over all of space. For the potential, well, I mean, all that the potential does is to add an extra factor V. So basically that would only increase the exponent of the V here by 1, and that's then already contained if we have these integrals. And for computing the latter kind of integrals, we are just using Laplace AB as Laplace AB plus A Laplace B plus 2 grad grad. And with some straightforward calculation, we basically get these relations here. So this is really not very deep, straightforward to do. And what one also can do is one can actually work out the explicit form of all the matrix elements which we then encounter. So with these identities, we can reduce all these gradient and Laplace expressions to just polynomials in U and V multiplied by E. And well, the matrix elements, they have two factors of this E clearly, and then some power A of U and some power B of V. And if I just work out all these matrix elements, then this is effectively reduced to an exercise in combinatorics, and one finds this is pi to the third A plus 2B plus 2 factorial divided by B plus 1, and then 2 to the power 2B plus 1. So that's pretty straightforward. What we then can do is that we pick some maximal coordinate power for the factor that multiplies our E. And here for this calculation, I've gone to coordinate power P equals 100. And we are only considering quantum states where 2A, so A was the exponent of U, U is quadratic, plus 4B, B is the exponent of V, V was quartic, where this is at most P. So I'm basically going with basis functions that are all of the form polynomial of degree at most 100 in coordinates times this exponential E. So with that basis, we also need to evaluate the kinetic energy, and here, since we don't want to leave the subspace in which we are working, we are using this standard approach that in particular in finite element computations one would also use. We are shifting one of the gradients over so one of the derivatives from the Laplace operator over to the left-hand side, and since everything decays towards 0 exponentially, we can do this. So this is straightforward. Now, in total, how many quantum states do we have to take into account? This we can work out with a bit of combinatorics. And here we find that if we are going for maximal coordinate power 4n, then in total there will be n plus 1 squared quantum states. So that's the dimension of our Hilbert space. I said for this calculation, I went to maximal coordinate power 100, so n is 25. And the dimensionality of my Hilbert space then is 676. So my Hamiltonian, my potential, and also the Gramian from taking the scalar products of basis matrices. All these are 676 by 676 matrices. The only problem is that if we look at this IAB again and actually look at the structure of these matrices, then it's clear that we will have to do the calculation with enhanced numerical accuracy. So this is not something one could do with base 64-bit IEEE 754 floating point numbers. That wouldn't work. But this is not so surprising. And basically, we already have that function with that problem with Legendre polynomials. So that's really not unexpected. And then, of course, what we still have to do, these BAB that we defined earlier, as I said, they are not an orthonormal basis. So we basically have to find the coordinate transform that brings everything to an orthonormal basis. And as a starting point, we are given that Gramian. And with this, basically all the problems that we needed to address are addressed, and we get this nice ground state. Now, one could think about going to the second eigenvalue, and that would be the next lowest energy O3 cross O2 singlet state. But this might not actually be the first excited state of this quantum mechanics, which very much, I suppose, probably would not be an O3 cross O2 invariant. So for the hydrogen problem, what we find is, chemically speaking, we have the 1s orbital in the first excited state. You could say that should be the 2s orbital, but this is energetically, of course, degenerate with the 2p orbital. And this is due to the hidden O4 symmetry of the hydrogen problem. So I haven't looked into this, but to me it's not clear that from this restriction to O3 cross O2 singlets, we actually do get the first excited state then as well. We probably don't see it on that subspace. And with this, I basically have shown everything that I found, and I would say we can switch over to Q&A.